Ça donne ça.
Ouais.
Vous voulez plus zoomer, moins zoomer?
Un peu plus peut-être.
Un peu plus zoomé
les slides, ouais, quand ça en aura. C'est une personne qui parle par là.
Au milieu?
Sur le côté.
Sur le côté. Donc ici.
Voilà.
Ok. Je vais un petit peu dézoomer alors. Comme ça.
Ok. Comme la dernière fois.
Ouais. Ça marche.
Pleased to welcome you in Paris for this International Open Symposium, for 2 days of the International Open Symposium. So my name is Christophe Calvin, I'm working at CEA, Fundamental Research Division, and I'm also the president of the association, Aristotle Association, which organized this 2-day symposium workshop, and also the 2 days after dedicated to ADAC organization. So may I introduce François Lucerne and Thierry Stratsma, who are two of the co-organizers of this workshop. We have other people in the room who participate in the organization of this workshop. So welcome everybody. I'm sure and I hope you will enjoy this 2 days workshop, and as you will see, and I think you have already seen on the program, we have tried to focus on two main areas and themes for this 2 days workshop. The first one is concerning benchmarking, and the second one is dedicated to the software sustainability. So, of course, if you want to give some word.
I will talk about the logistic mainly. So you know where is the food, there will be no rush, and everyone will be happy. Quickly. Oh, sorry, Tiak. Yes, because we wouldn't be here without ADAC. So Tiak.
All right, I am Thierry Stratsma from Oak Ridge National Laboratory, and on behalf of the ADAC Governance Board, and ADAC stands for the Accelerated Data Analytics and Computing Institute, I'd like to welcome you here. This is the first time we do an open symposium as part of the meeting of ADAC, and the reason for that is that we want to engage other communities and not just talk amongst ourselves with the institutions that are part of ADAC about challenges in high-performance computing and hear from the different types of communities what their vision is on these particular challenges. And that's why we have this open symposium. So again, welcome on behalf of ADAC.
So maybe I will skip this part. You can find that back on the Association Aristotle website. So that's a brief describing of the benchmarking and why we are organizing this day. So in few words, we are all doing benchmarking here in this room. Thank you. The idea is that we have different usage, different needs, and so on. So let's brainstorm about all these differences and the common points. So clearly, the purpose of today. Why do I have that? Oh, that's not the correct slides. That's why. That's for tonight. Don't look at it. Okay, never mind. Okay. And then I should have something. Yeah, that's logistics. I spoiled myself. Okay, anyway, that won't be for 10 more, but that will be alright. This one is more important. You will have Wi-Fi and food. So as for the Wi-Fi, actually you have a Accor Hotel guest Wi-Fi. There's no connection code, you just have to connect on the Wi-Fi, you open a Google page and so on. Just say I accept and you're fine. All you will see today, included this, is on a Google Drive that you should have received. If you did not, please reach me out. So that's the agenda of today. Then we skip that, you have that on the internet. As for tonight, I created a Google Maps address, so you will find the restaurant address and this hotel address. So the food will be served right here in the back. You have a restroom up there. You can ask anything in the lobby. Should you be lost? And just the dinner tonight will be at Pavillon Puebla, Avenue d'Arcel. This is really inside at the entrance of the park of Butte-Chaumont. So I propose that we leave 6:45 tonight in the lobby of this hotel. For those who want to use public transportation, let me know if you don't have tickets. I can manage to buy some. I think that's it for tonight. So Wi-Fi, as I said, it's an open one. The participant list, unless you don't want to, but we would like to share the list of participants of today, so first name, job title, and organization, on the Google Drive. Again, if you don't consent, that's fine. Just please mention it. During the conference, there will be photo, video recorded. So by participating to this workshop, you agree to smile on the picture. And there are some advice if you want to look like a French on the picture. So security, this room will be locked if we have to go out and so on. Christophe and I, and Katia, that I don't see, she must be upstairs. We will have a card to close the room or open it. So if you need something, you let us know. And also on the Google Drive, because you're also here to have some fun, you will find some nice places that I recommend. Don't judge my taste, okay? That's on the Google Drive, so if you want to use it, please go ahead. And, well, yeah, some context, I think we said that again. Let's skip that. Let's skip again. And yeah, that's the most important. Thank you for your attention, and on behalf of ADAC, Aristotle Association, and CUR, thank you very much for attending. Okay, so let's welcome, give me a sec. Let's welcome our first speaker. So Sanjay, Senior Director of CDAC.
Good morning all. First of all, I would like to thank ADAC for giving us the opportunity to present what we are doing in India regarding HPC. And so here I'll be talking about supercomputing mission, what India is doing currently, briefly about that first. And then later on what kind of activities we are doing in the system software, system management, benchmarking and application software. So that will be the brief about what we will be doing, what we are doing and what we will be doing in this mission. So first of all, I would like to introduce myself. I am Sanjay Vandekar. I am a Senior Director at CDAC and heading the HPC Technologies Group. I worked in HPC area for a long time, almost 20-25 years. I'm actually a hardware developer. I started way back in 1990 developing the transputer-based supercomputer. So that was Param 8000, the first supercomputer what CDAC developed. And over the period, we have reached to now this stage where we are actually going to develop a 20 petaflop system based on indigenous technologies. So, brief about CDAC. So, as I told you, 1988 CDAC was established to design and build supercomputer. And over the period, the CDAC is expanded into many other areas other than HPC. So we developed microprocessors of RISC-V, and we are planning to develop ARM-based HPC processor. We work in the strategic electronics, software technologies, health informatics, cyber security, multilingual and heritage computing, as well as education and training. So that is a brief about CDAC. About NSM, we started some time back, about 6 years back, 6 to 7 years back, on this mission. And this is a funded project from Government of India. 2 ministries, Department of Science and Technologies and Ministry of Electronics and Information Technology is funding this project. And CDAC is the main implementing agency, along with the Indian Institute of Science, who are mainly handling the research projects in this program. So under this supercomputing mission, we are working on the 4 pillars of HPC, basically the complete ecosystem, starting with the building of supercomputing infrastructure, then development of indigenous technologies, applications of national lead in few domains, as well as some research projects in the application side, and human resource development. So these are the 4 major pillars. Till now, we have put up about 15 supercomputers under this program with a 24 petaflop of compute power. So we are working in the phased manner to basically develop this ecosystem. So phase 1 and phase 2, we actually assembled and manufactured systems within the country. In phase 3, we are actually building the technologies also, from servers to software stack and even the network also. So in phase 3, we are going to put up about 9 supercomputers with a compute capacity of 40 petaflop. Again, this is actually, the work is ongoing, and the largest machine will be about 20 petaflop, which is going to be a national facility. So till now, these 15 supercomputers are being used by about 6,500 plus HPC users from more than 120 plus institutes across the country. So these are distributed systems, multiple places they are there, and the local institute uses about 70% of the compute power, 60% of the compute power, and 40% is for the national users. So that is how the split is done. And all these systems are managed by CDAC. So more than 500 plus PhD students are using, and they have already published about 850 plus publications on these systems. So I'll talk about these other things in the next few slides. So these are the 15 systems at various places, at various capacities, starting from 838 teraflop to about 5.2 petaflop for compute power. We have actually using about 70% CPU only combinations, and 30% is a GPU combination in terms of compute power, as per the requirement of the users here. And slowly we are trying to increase the GPU percentage as and when the applications are getting mature for the GPU requirements. So the largest machine, which is a 5.2 petaflop, we call it Param 6GI, is a national facility which is used for both HPC and AI requirements. So this facility further recently upgraded using another project called Airavat, and now this facility is having sustained compute power of 8.5 petaflop. And this is the 75th position in the latest top 500 list. And this particular system is used by about 600 plus users from 100 plus institutions for both HPC and AI requirements. On the indigenous development, we are developing various technologies, starting from servers, which are again specific for HPC requirements, very dense form factor, about half width, 1 U form factor, one server is there, with a centralized power, 12 volt and 48 volt. This is what we are actually trying to use. Again, this will be liquid cooled with the DCLC technology. In one track, currently we are putting about 35 kilowatt of power. We are also planning to develop a HPC processor, which is ARM-based thing. Some work is already started on this. So latest core from ARM, Neoverse V2, is planned to be used in this. About 96 core processor is getting developed under this program. Third thing is Trinetra scalable HPC network. This is a low latency, high speed network. Currently we have a card here on the right side. Here. This is actually having 10 links which is coming out of this card. And this can be connected in various topologies, including 5-dimensional telephone technology. The complete hardware and as well as the software is getting developed. Let's see that on this. On the system software side, we are using mostly the open source tools and technologies, and they are getting tuned as per the requirement of the system. More slides will be there on this. Okay. Then we are also working on storage. This is dial-based flash storage. This is just started. We just recently started this work. As I told you, liquid cooling technology is very important for our requirement. So we are spending some R&D efforts on this also. So this is a software stack. What is there in all the 15 systems is uniformly there on across all the systems, so that the users can migrate very easily from one system to other system. So this is the standard what everybody uses. Apart from that, we have put our own tools and softwares which are actually complementing this open source software stack. The right side you can see there is tools which are there, various tools are there. There is a debugger is there. Then this is again a crane is mainly for nav user, where you can they instead of using the command and option, they can use the basically GUI based thing. So and there is a workflow also you can manage this crane. Then C actually is more details are there on this side. Then we have some automated scripts so that the cluster can be built very fast. So we can build the cluster within a week's time, even though thousands of nodes are there. So that is what the scripts and other things can do. So in C Chakshu is the central portal where you can do user creation, accounting, billing, ticketing system, and which is handling more than 6,000 users currently. And it can monitor all the systems centrally. On the application fronts, because all the systems are there at various places and users need to migrate from one to other as per requirement. So we have actually ported and customized the applications as well as tuned the application performance of various open source applications in various domains. You can see the list here. Apart from applications, we have visualization programs, dependency libraries, programming models, again common all across the systems. Then we have various frameworks available of the systems, AI, ML, DM tools and technologies. So to support the users, we have a separate team who can actually support the users in terms of supporting, tuning, and accelerating the applications on these HPC systems with latest technologies. So this team actually evaluates the newer technologies as well as they do the benchmarking, port the new applications on those systems and those different architectures. Again, they do the optimizing and scaling of the applications depending on the requirements. As well as there is a training part is also being done by this team so that it can proliferate HPC across the nation. So under this program, as I said in the first slide, we have various HPC applications are getting developed, which are of national need. So main purpose of this program is to have the ready application for the end user. So you can see here that there are 4 applications. The first one is basically genomics and drug discovery tools are getting developed under this program, which are required for the domain users. So the domain users can straight away start using these tools, and they can use this HP system without knowing about how to use and how to program. Second program is on the urban modeling, which is actually a decision support framework to address urban environmental issues like weather, urban floods, and air quality. Again, this is developed as the end user in mind, and it has all GUI and everything. Third application is on the flood early warning prediction system for river basins of India. And fourth one is seismic imaging to aid oil and gas activity. So you can see here, apart from CDAC, there are domain people or domain institutes are getting, they are working with us. So that is the model what we follow in CDAC. So we support the users in developing the application, and the domain people will collaborate with us from the domain side. So that is how most of the places we are working together. So more details about this NSM platform for genomics and drug discovery. Here there are 2 major pipelines are getting developed, and the tools required for this pipeline are getting developed here under this program. One is drug discovery pipelining, which starts from providing the system to the end user, which has this pipeline, and to support this, with various tools which are getting developed under this program. Second one is on the genomics pipeline. Next application is on the NSM urban modeling, which is an integrated system, which has back-end side, there is HP system with coupled model simulation platform. And on the front-end side, you get a decision support and dissemination system for early warning advisory and data analytics for weather, flood, and pollution-related requirements. And there are many users are there, starting from government bodies, researchers, disaster management authorities. So the complete software is getting developed, keeping the end user in mind. On the early warning system for flood forecast, we are using Anuga software, and currently a pilot is on one of the river basin of India, which is called Mahanadi River, and currently 3 days flood forecast is being given based on the regular runs of this Anuga on this data available from the Central Water Commission of Government of India. So end user is actually checking whether the data and the output of this program is basically matching with the actual field conditions. So that is going on right now. The last 2 years this is happening, and we are tuning the performance of this application. On the seismic image software, again we are working with ONGC, that is the oil and gas company in India. They are giving the data, and this software suite is getting developed based on the data and the feedback from the end user. On the HPC aware manpower creation, our target is about 20,000 HPC aware manpower to be trained under this program. Till now, about 19,500 manpower has been trained with various types of courses, starting from short term, where we conduct various workshops, boot camps, hackathons. Medium term, there is a 6 months course also is available, which we call it as a PG diploma courses. Again, this is going to be not only programming, but domain specific training is also being done. Then some formal courses also are being conducted at educational institutions. So this program supports this educational institution in terms of creation of the curriculum, as well as giving access to the systems. So we have various nodal centers who are actually helping us in training these people at various Indian institutes of technologies at various places, Kharagpur, Madras, Goa and Palakkad. So these 4 nodal centers are helping us in creating this methodology. We are also collaborating with Intel, NVIDIA, OpenACC and ANSYS. So they also work with us in this manpower, along with the workshops and boot camps and hackathons. So this is a brief about what we are doing in NSM. So some of the specific work I'll showcase here regarding system software, system management and benchmarking and application software. So this is the C-Chakshu, which is a multi-cluster monitoring platform. You can see here, on the right here, that all the systems which are available in the currently under NSM 15 system, we can see live here how the utilization is happening and whether any issues are there. So we can monitor central places with this tool. This tool works on the local site also, so they can see the individual site of their own. But at central place, we see the complete picture of this NSM systems. So basically, it has a live dashboard which can monitor nodes, infrastructure, jobs, how many jobs are running, what kind of job they are running, what type of job they are running, what are the users, you can manage the users, different utilization of CPUs, GPUs, and various services on this systems, and interconnect health. We can analyze with the historical usage data using this tool. This tool also does job accounting and reporting. Again, we are planning to use this data for forecasting usage, for further usage, and how to basically have a policy decision based on this. So apart from this, this tool is actually at user level also it works, where the user can see how his program is working, the real-time performance. So way back in 1990, those days this kind of tools were not available. So we used to see the performance of our vertical nodes using LEDs. So how the LEDs are working. Based on that, we used to see whether my program is actually utilizing the full power of the CPU or not. So the similar way here, user can see different nodes, how they are getting utilized live. And he can see whether at that moment, and he can have some prints in his code where he can see at that moment what is happening on the node and what nodes are getting utilized, and what is the percentage utilization of each of the CPUs, how much memory is getting utilized. So this way he can see live interaction with the system and find out whether any bottlenecks are there in code. So this is a very useful feature because every user is not comfortable with using the performance monitoring tool. So this is easy for the some of the users who can utilize this system very effectively. So this is, C-Chakshu also has integrated ticketing system where users can raise the tickets depending on what kind of problem. It has a database also where the previous problems faced by users and their solutions are given, and people can go through that very easily. As I told you, we are working on OHM HPC processor, which is an ARM-based processor, which is planning to come sometime another 3 years down the line. So we have started working on the ecosystem for the ARM-based requirement, and we already have one small cluster of A64FX supplied by Cray. About 32 nodes we have, and we do all our experimentation on this cluster. So currently work is started on SYCL compiler as well as SYCL profiler and debugger for ARM-based. So this is just recently we have started this work, and we have a team here who can answer your questions, and we can interact what kind of work we are doing on this. Apart from that, we are working on compilers, like GCC, optimization of that, and LLVM compiler also for this. So some work is presented here, where some GCC optimization is done with the help of performance library-based plugin, and the difference we can see here. The GCC, best GCC was giving about this kind of performance with 49 seconds for this particular GEMM code, and with FCC, that is the Fujitsu compiler, is about 5.7 seconds it was taking. With this plugin, we could actually reach here to the FCC. So this way, we are trying to see whether we can optimize the open source code, open source tools for this ARM-based ecosystem. On LLVM also, initial some results are here. We actually tried to put one external vectorizer with the LLVM, and with that we could get very good difference in the performance, about 5 to 7 times better performance on GEMM. Some work on MPI library, MPI and match library is also going on here. Including AI/ML libraries and packages. So some results are shown here on MPI collective calls. We have done some optimization with basically enabling vectorization in these calls. These are some results on libraries, MPI libraries, match libraries, and AI/ML libraries. So we could get some performance differences based on the optimization we are trying till now. As I told you, phase 3, we are actually developing the systems with our own technologies. So one of the system which is very specific to one particular application, which is real-time processing of radio telescope GMRT data with HPC and AI application. So this we are working with NCRA, TIFR, and here this system is actually going to take the real-time data from the antennas, GMRT antennas. About 16 channels will, with 1.6 gigabyte per second, will be coming live into the system. This is coming on 10 Gbps Ethernet on the fiber from the antennas. And the data will straight away go to the servers which are having 800 GPUs. 200 GPUs per server. About 20 servers are connected in the front side. Then this processed data goes to the second level where transient detector is there, where 20 servers will be processing the data further. In between you find some transient triggers. That data is saved onto the 2 petabyte storage which is connected over InfiniBand. So this InfiniBand currently is 100 gigabit InfiniBand switch. So there are 3 stages here. You can see the final stage is imaging and confirmation stage. So this is one important application which is going to be developed under this program along with the system. So this system is getting deployed now. Another 6 months this system will be live we already tried certain servers on this live environment, a few servers to check whether the things can be done at real time. On the application optimization front, as I showed you earlier, one application which is related to flood forecast. We are working on Anuga. These are some results. Initially, the code was working only at 8100 square meter resolution, and now we could tune the code and optimize the code so that we can work at 300 square meter. And we have planned to make it about 50 square meter resolution. So these are certain results here. Earlier it was taking quite a high time. Now I think we are able to do the things in 300 square meter resolution at 4.6 hours. The data, which is actually of 11,372 square kilometer river basin, that data is there, and that data is getting processed in time of 4.6 hours using 96 nodes of 46 core each. This is currently working on CPUs, and we plan to port it on GPU also. So that work is also started recently. And this GPU porting optimization is in collaboration with Dr. Stephen Roberts, which is, I think he's from NCI, and Ole Nelson. These are the two people with whom we are working currently. So here are some results on this Anuga. Initially, as I told you, we were working at very high, means resolution was very low, and now we are actually have some results with 100 square meter things. So various optimizations are done, and the memory optimization, because initially with high resolution the memory of per node was actually very less, so means it was not able to run time for single precision and double precision, mixed precision basically, wherever possible. We also would like to work on Triton. We have just started working on this. Again, it is for the same flood simulation. And our team is able to work on CPU-based system, but GPU, I think, we are not yet successful in working this program, this application on GPUs. So we would like to work and collaborate on this Triton-based tool also. On the exploration of various technologies, we are exploring SYCL on the SYCL for our own requirement. One of the requirements is on the seismic code, which is the SYS Echo Mod 2D code, which actually is ported on DPC++, that is SYCL. So these are some results here. Initial code is available on CUDA, and now we could convert into the SYCL, and that is running on both CPU and GPU as well as A100. You can see the performance here. The same, the SYCL is giving same performance on A100 compared to CUDA, and on Intel PVC, it is actually giving 1.7x performance. And we plan to basically use the same SYCL code for other technologies like AMD and AMD GPUs, as well as FPGAs. Some exploration on codes, which on the different architectures. ARM, as I told you earlier, we have various platforms available with us. So we tried on ARM. Baseline results are given, and we propose we could get better performance on each of these platforms. Then next one is related to various computer architecture exploration. Right side we have actually done some exploration on A64FX system. What we have about 32 nodes of this. So we tried various applications of open source, NAND, LAMPS and so on, and ported and checked the performance as well as the results. So various capabilities of this platform like HPM and other things are right. We have some challenges in the compiler side. So we earlier using Cray compilers because we didn't have access to Fujitsu compilers. So that is where we started working on this compiler side. We also have worked on AMD GPUs and comparison with the NVIDIA GPUs. We have done some exploration on Julia also, and these are some various results on this Julia platform. We are also working on some finance domain exploration, and basically some of the application software, open source applications software, we are actually trying on our systems for credit risk assessment, cyber security, fraud detection and so on. So these are some results here, and trying to see this ecosystem is available on these ecosystems. Our team also works on AIML DL on the systems, mainly basically providing the tools and technologies on these platforms, as well as we have some specific products also where people can start using from day one this kind of systems, because we give the ready environments. So that's the Param Shavak system, which is a system where we give the complete software stack. On the R&D side, we are actually having some work on identification of malicious user login activities in Microsoft cluster. So we get the data, we are trying to analyze that and see whether we can do the user behavior analysis. Similarly, on code identification also, what kind of, whether any malicious codes are getting executed on HP system. So this is again getting work on this system. We also work on the benchmarking and profiling of various benchmarks which are there available on this domain. On the bioinformatics activities, we have actually a very good team here. Utavesh is here. Maybe we can discuss with him more detail on these activities. We provide a bioinformatics resource and application facility to the end users, where the complete tools are available. Our team supports them to utilize the domain people so that they can use these systems in applications. So this team also does the software development in various areas and do the domain-specific research work in computational genomics, molecular dynamics, molecular modeling for cancer proteins and protein misfolding and so on. So this is a tool, one of the tools which does basically NGS analysis, is a workflow, and again this is ready to use software tool available. There is another tool which is high throughput confirmation generation and docking tool, we call it Tango. We are actually open to use NWK, which can add value to this Tango based confirmation search. Again, there is another tool available which is visualization and analytics tools. This is actually a parallel visualization. One can see multiple views which are required to be seen to analyze the output of the programs. We are also working on some lightweight molecular dynamics simulator development. So these are at a very initial stage. Currently we have developed all the modules, but they have been getting optimized for the scaling and better performance. So the same tool actually can utilize at the back end FPGA-based accelerators. So this is some work is going on where some of the code can be actually put up on the FPGA. So your right side you can see we have a Intel Agilex FPGA with a DDR2 bit and multiple 100 gigabit links which are coming out out of this. And multiple of such FPGAs can be connected together to process this molecular dynamics codes. So during pandemic, actually we have utilized these param-MSM systems for COVID-19 studies. So in April 2020 itself, our team could find what are the possible drugs which can be utilized using the drug repertoire. So these are some 3 drugs our team has found out in sometime in April 2020, within 3 months time when the pandemic started. As well as some traditional medicines also, how they were useful for this COVID-19 were also analyzed using the same tools. We could find some Ayurveda molecules which are actually useful for this COVID-19. So thank you very much for your patience. I think I covered too many things, maybe. So I have a team with me here, so you can actually discuss in detail about the various topics I discussed during this presentation. Thank you very much.
Is there any question?
Thanks for your presentation. I apologies I arrived in a little bit late, but just caught the end of your mentioning of the work that you're doing with the Anuga code.
Yeah.
So, as I understand it, originally the Anuga package was developed by a team at ANU, and we were really delighted to have a team from CDAC come down to the hackathon late last year at ANU, and I think a lot of good progress was made in terms of adapting and developing that code to run more efficiently on GPUs. So hopefully soon you'll be up and running and large scale on the GPUs as well. Thanks for sending the team down.
Yeah, thank you very much. I think we are, as we told you, that our team actually visited Australia in the hackathon and they really did good job along with the team there. And we are happy to work with Anuga team to optimize and put it on GPU. Thank you.
Hi, over here. Yeah, thanks for your presentation. I was wondering if you could comment some more on the specialized processing you're building and kind of what the motivation is for that. Are there specific features you're adding or other capabilities that you found need that aren't available in the commodity processors?
Yeah, you're talking of our own processor? Yeah.
Yes, sir.
Yeah. So mainly, as I think there's a lot of discussions happening, the memory bandwidth is one of the major challenges in any HPC processor. So we are actually planning to have HBM on board, as well as certain features which are actually getting discussed right now to add to this processor, which can help the end user. So some of them are like having vector-related optimizations, where we can use it from 8-bit to 64-bit. That is one of them. And there are some more things which I am not actually directly involved in that, so I don't have the complete details on that. But we are open for, because since we are just starting, we are open for any inputs from the community. We can actually add certain features, if it is feasible within the time frame. Yeah.
So maybe a follow-up question in that direction. So you mentioned the FCC compiler. You said that's the Fujitsu compiler, right? Did I get that correctly?
Yeah.
So what's your relationship to Fujitsu for the processor design?
No, we don't have any relationship actually. We actually purchased the system from Cray. So Cray was supplying the system, and then because since we are also planning to work on ARM-based clusters, so we purchased the system so that we can start development on software ecosystem.
Any other question? So my turn.
Yeah. Thank you very much.
Okay, just one more.
Yeah,
So,
yeah.
at some point you mentioned software to monitor the usage of HPC system and increase also distribution of job and something like that. You have also the monitoring for the data usage, because you can use the sphere logs, for example, to improve the usage of your HPC system.
Yeah.
Do you have the same concept for the data usage?
Yeah, so as I showed that we are trying to use that data for using AI/ML tool to check out what kind of usage are there, what kind of problems are there, how people are using it, whether they are effectively using it. Some people actually put up very large running time, even though the program runs for smaller duration. Those kind of things are there. Then basically whether they are really using the full allocated resources. That is another thing which we check it. Some people will use 60 nodes for 100 nodes, but actually effectively they are using only 60 nodes. So that way we can actually find out using these slum logs. So that work is also started based on the historical data what we have.
And the second question is about the mathematical libraries you are improving, working on optimizing this ARM. Is it something open source?
Open source, yes.
Okay. Any other question?
Thank you for the interesting talk. So, just the information, you are going to develop your own processor. In that case, I used to work with developing some stuff on the capability that also some make a progress, some demonstrations such as its compiler. But some information, maybe you can access GitHub on Fujitsu. So there is some micro-architecture detail can describe in GitHub. So if you want such kind of process architecture, so please see and document how to tune such kind of ASIC Linux program. Sure. I think we'll be in touch with you and contact you for the more details. And definitely we'll be happy to utilize and work together so that we can actually make this ARM-based ecosystem very stable. Thank you very much.
Thank you, Sanjay. Thank you. So our next speaker is Estella, Head of Division of Novel System Architecture Design at Forschung Center.
Hello? Yes, it works. Okay, so thank you very much, Franz. Thank you for the invitation. I will speak about benchmarking in the context of co-design, and in particular in the context of two projects in which I am involved. So that's the outline. I will first define what I mean by co-design, since this is something that people understand under different meanings. What is the role of benchmarking in this context, and then I will share some of the experiences we have in these two projects. So first, what I mean by co-design. So what I mean by co-design is studying the relation between these four elements, between the application code, the software stack, the hardware components, and the system architecture, searching for which are the required or the needed modifications at each of these four levels to achieve the overall best performance and energy efficiency. And when I say the best performance and energy efficiency, this is not only for one specific application, but potentially for a workload mix. So trying to find the sweet spot between these four elements that gives the best result. So benchmarking plays a very important role in all four steps. So on the application side, we use benchmarks to characterize the applications. We do this by selecting representative synthetic benchmarks, mini applications, and large-scale use cases. On the software side, we do benchmarking to evaluate different versions of the software and also different options. So think about a project in which we develop software elements, so system software. We do periodically new releases of the software, new rollouts on one platform, and every time there is a new rollout, we have benchmarking campaigns to measure what has been changed with respect to the previous version in terms of the impact, positive or negative, on the applications. We also use benchmarking for comparing different hardware devices. So we run on hardware prototypes, we run on reference platforms, and also not only running the benchmarks on the systems themselves, but also through models and simulators when the hardware is not yet available. So when you are developing, for example, a new processor, and this chip is not yet being produced, you do this through simulators. And last but not least, we also use benchmarks to determine which is the best combination of resources in the overall HPC system for a given workload mix. And I'd like to highlight that we look here to a diverse application portfolio. So it's not an application-specific solution. We are looking here for a workload mix typical on an HPC center such as the one at Lille. So that is the role, the very important role benchmarking plays in the context of co-design. And I would like then to go a little bit in some of the experiences we have through these two series of projects, the DEEP projects and the EPI, the European Processor Initiative. I will not describe the projects themselves in detail, I just want to give you enough information so you understand what is the different context between the two projects. On the DEEP side, the focus of those research projects is system-level architecture. We have developed there what we call modular supercomputing architecture. I just have one slide on this later on. On the EPI side, the European Processor Initiative is aiming at developing an ARM CPU and accelerators based on the RISC-V ISA. So here the work is at chip-level microarchitecture. This translates therefore in different activities through these projects. So on DEEP we do hardware prototyping, so we deploy a medium-sized cluster between 100 to 200 nodes. We do system software development and we also do application porting, but we are speaking here about full-fledged applications, so real use cases. On the EPI side, the main focus is chip design, chip emulation, and then ending on the tape-out. There is software development, but typically low-level software, so compilers and things like that. And then we also do benchmarking, but we use here rather small benchmarks, small mini applications, not so frequently large-scale applications. In terms of application selection, on the DEEP projects, we have always done this as part of our proposal. So we put the project together, we decided what are the use cases we want to look into, and we selected 6 or 7 of them. We took the partners as partners in the project, and these codes were always large-scale codes, so large-scale applications that are also running on our machines, aiming at covering a variety of scientific fields, as I said, a mixed workload. On the case of EPI, this selection was done within the lifetime of the project. It actually happened, if I remember correctly, during the first 6 months. There are about 16 partners involved, and altogether we end up with a benchmark suite that contains more than 40 codes. These are mostly benchmarks, mini applications, and kernels. We do have a few large-scale applications, but the focus is on the small side because we are looking here at the processor level, so that at the small scale. And also here we can try to cover a variety of scientific fields. So these are the two projects that I will be speaking about. And I will start with the DEEP projects where we do co-design and benchmarking at system level. We developed in this project this modular supercomputing architecture, or MSA, where the idea is you build an HPC system not just as a monolithic machine, but as coupling different clusters, so coupling these modules. Each one of them has a different node architecture. So you have a module that is only made of CPU, so CPU-focused cluster. Then we have this, what we call booster. This is a cluster of accelerator, mostly GPUs are there. And then for data analytics, we have a module that is a highly heterogeneous node with a strong CPU, several accelerators, and then a large volume of memory. So, okay, the concept itself allows also to integrate disruptive technologies, but in the context of the project I was speaking about, we deployed a prototype that contains these 3 compute modules plus the storage. And the goal in the project was to define the specifications of this machine fulfilling the requirements of the application use cases we have involved in the research project. When we do that, when we apply co-design, the question is, okay, we do have some parameters which are fixed, and we do have some parameters of the design that we need to decide on based on co-design principles. The fixed parameters I listed here, so okay, we decided this is part of the project, this is the architecture is settled. We have also design targets for the 3 modules. We want on the cluster to have the highest possible byte per flop ratio. We want on the booster to have the highest possible energy efficiency. And on this data analytics module, we want to have the highest possible flexibility and also memory. These targets aim at addressing parts of our application portfolio, so typical kinds of applications that fit more or less in some of these 3 categories. We also had fixed the installation time, so we were sure we want to deploy this machine, it was in 2020, we had a fixed budget, and we also knew where were the providers, these were the partners in the project. Now, what are then our design choices? So we still need to decide on what is the number of nodes we want to use in each one of these modules, also therefore the relative size of the 3 modules. We want to decide then on the node design itself, so on the cluster you need to decide the CPU type and the SKU, so number of cores, DDR, etc. Also frequency, for example. Booster, the CPU type and also the type of accelerator and the number of accelerators that you had per node. And on this data analytics module, the same thing, the CPU and also the accelerator type. So these are the parameters we want to fix based on the requirements of the applications. In order to do that, we have this selection of applications. We analyze them through performance analysis tools to characterize the applications and understand the requirements. Based on this, we define the architecture of the hardware and the software, of course, also fitting in what are the available technologies. So one thing is what the applications would like to have, the other thing is what is available in the market to best match these requirements. So we try to make a kind of fitting between these 2 things. And with this, we fix then the design, we fix all these parameters I mentioned before. This we give it as information back to the application developers so they can start already preparing their applications, making adaptations if they are needed, at the same time as we work on building the hardware prototype. And once the hardware prototype is there, we use again the applications to evaluate this hardware. So benchmarking is crucial in all this left part of this graph. So it's crucial for the analysis part and it's crucial also for the evaluation part. So the steps that we applied to be able to give this co-design input was first we defined use cases representative of each one of the applications, including of course data sets. And thinking about that sometimes we need different use cases, so not only one per application, but maybe 3 or 4 different sizes, so we can do node level and also system level benchmarking, for example. We integrated those codes in a benchmarking environment, and we use Nuke, that is an open source solution from Unix. We run then the use cases on representative hardware, so we are thinking about building a machine. We need to see how they are behaving on, let's say, current generation hardware. And then we perform this performance analysis and measurements in order to extract quantitative co-design input. What the examples of this, so we looked into compute-intensive kernels to understand what is the ratio between CPU and accelerator parts. We look into the performance and the scaling behavior of each application part to define then the number of nodes we need per module. We looked into communication and I/O to determine memory and network bandwidth, and then also on the balance between computation and communication to settle things like which is the ratio of number of cores and memory bandwidth, and also which is the ratio between the performance on the node and the network communication capabilities. Once this is done, so with all this information, we finalize then the design of the prototype, and then at the end when the prototype is there, we rerun these steps, the 3 and 4, comparing with the baseline. And one important thing I'd like to highlight is that the code itself also changes over time. So we are speaking about a time frame between 1 and 2 years from the time we provide the co-design input and the time the prototype is being deployed. Therefore, the application developers have been working on the code in this time. So there is the baseline is not clear to establish. So there is kind of a moving target in both directions. The result of all this work has been the deepest prototype. This is this machine here installed at Jülich. We end up with 55 clusters, 75 booster, and 16 data analytics nodes. And just to overlay some of the details of the node configuration, so we had Skylake on the cluster, we had Cascade Lake on the booster and the data analytics module. And in the case of the booster, we had one NVIDIA GPU per node. In the case of the data analytics module, we had one NVIDIA GPU and also an Intel Stratis FPGA per node, plus a bunch of memory. So here we are speaking about 3 terabytes of non-volatile memory as we look into applications for data analytics. So that is the final configuration. The system is then deployed, and then comes the last step, which is the evaluation. I give you here only one example. This is an evaluation done by an application for space weather from the KU Leuven. This application has two distinctive parts. So it has a field solver and a particle solver, and the goal of this evaluation was to find out, should we partition this code between cluster and booster, or should it run on only one of those modules? And because these two distinctive parts have different running behaviors on CPUs and GPUs, we end up with the conclusion that splitting the code brought a benefit in performance of, in average, something like 30% when you do the partition, better performance. So again, this is again benchmarking. So this is again measuring what is then the behavior of the application under different system configurations. So all this was at system level. Now let's look when we work at processor level, and that's what we do in the European Processor Initiative. So here we also have hardware platforms, so we have reference platforms, so other machines as A64FX, for example, it was one of the machines we were using. We also have software development vehicles in which there is an FPGA-based implementation of the design of the chip, and then later on in the project there will be then this EPI prototype. We use benchmarks for validation, and we also use benchmarking for co-design. In this context, it's based on simulators, and I will speak about this. So that's what makes a difference when you work here at the processor level. What we learn, we give feedback to the architects of the ARM-based chip, this is called REA, and also for the architects of the accelerator, of the RISC-V accelerator, that is called APAC, and they use this on the design of the next generation chips. That's also something to highlight. When you speak about co-design, time frame plays a role. So you are always working, what you provide today can only be taken into account for the design of the next generation or the next to the next generation solutions. The scope of co-design was always focused on giving quality feedback to the hardware and software designers. So we are speaking here about co-design between application developers and chip designers. We use for this a multi-level suite of benchmarks, so starting by full applications, but mostly focusing on benchmarks and also synthetic benchmarks and mini applications extracted from these full applications codes. These are running then through simulators and also running on reference platforms. This is this multi-level approach with models and simulators that starts at analytic levels, very high level, simulators like Game5 and reference platforms, which are equivalent hardware available today, which is more or less close to what the project is developing. So something like A64FX or Gravity. By running these benchmarks and mini applications through the simulators and platforms, we can analyze the impact of the specific design parameters on the application performance. And putting this together with the technical and the cost constraints, the developers of the chips can then come up with a processor design that then we give back to the application developers so they know how to optimize the code. The benchmark suite in EPI is very large, so it's over 40 codes covering a very wide variety of fields, but also with a quite comprehensive reference benchmark suite, so typical benchmarks of HPC, HPL, HPCE, Stream, all that, we are using all these things. And we are using them to run them through simulators. This is one example, the one in which Jülich is responsible for. So we have developed a Gen5 simulator of this ARM-based chip from EPI, from REA. So you see there a detailed representation of all the chip elements, like the CPU core, the caches, the network on chip, the memory hierarchy. And the module does not only represent them accurately, it also allows you to play around and to change things in this change these parameters to play around what happens if I have more cores or the cache hierarchy is differently, how does this impact on the applications? So yeah, well, that's the contribution of Jülich, analyzing the design trade-offs with benchmarks and giving them the feedback to the chip developers. Examples of how we have used this GEM5, just 2 of them. So we can use GEM5 to do things like evaluating prefetchers. So these are 3 different prefetchers, and we played here with 6 different mini applications or benchmarks. And we will see, comparing with the case in which you don't have any prefetcher, how does the speed up? So what is the speed up gained by each one of those, using each one of those prefetcher mechanisms? Another example, you can also use the model to do roofline analysis. So this is the roofline of, in blue is Graviton 3, in red is A64FX, and in green is what we obtained from the GEM5 simulator for the EPI processor. And then we can place different benchmarks like HPCB or Mini-FE in running on different configurations, how they land on this roofline. We have done many other analyses, such as what is the number of VNets for the network on chip that provides the best communication performance and so on, but these are just 2 examples. Another example here is on application evaluation, and this is work from the from the Instituto Técnico de Lisboa in Portugal. They used mini-ghost and they compared running on real hardware on Graviton, that was Graviton 2, in AMD and on Intel Xeon Platinum, and then comparing with the GEM5 model. So this allows you to study things like how does this scale with the number of cores, and to see that, okay, the model is not perfect, it kind of underperforms against similar microarchitecture, and that's always something you have to keep in mind. So models can give you an idea of trends, of what happens, what are the general trends when you change something on the architecture, but they will not be 100% accurate. So that's something you have to keep in mind when you try to extract conclusions from them. Yeah, what have we learned with all that? So that's getting to the end of the presentation. So we found numerous challenges, and I just classify them here under technical or practical, and then more strategic or logistic. So on the technical side, we found it was very hard to extract quantitative co-design input, and it does not help just to ask the developers. So most of the time, the application developers don't know really quantitatively what their code needs. It's even harder if you are not looking at individual applications, but at workload mixes. You don't really have a clear baseline. So you are in a moving landscape in which the application is evolving over time, the system software is evolving over time, and the hardware is also changing. So you do benchmark today on a given hardware, you try to learn how will the new version of the application or the new version of the hardware with a different software stack behave, and that's not straightforward. It's also hard to pinpoint and quantify the precise effect of co-design on the design decision. So that's something we are always asked by our reviewers in our projects. So, okay, you provided co-design input, how did it change on the design of the final product? And that's not just a straight line. So the designers need to take inputs from many sources into account. There is also cost-driven decisions to be taken. And there is always this playing the role, the time frame in which you can really apply this co-design input. You are not working for the current generation, but for the next or next to next. On the logistics side, one systematical or let's say structural issue we always faced is that application developers are rewarded for scientific runs. They are not rewarded to do benchmarking or to do co-design. They get the scientific papers, they get their career paths through scientific runs. So for them it's kind of going out of the way to work together with us. And that's an issue we are often facing. Also, more on the kind of practical or political way, sometimes in these projects you do the code selection. It's not only based on pure scientific criteria, there are also politics and relations there that they play a role. And one thing we often have the experience, especially when you work at component level, at processor level, some details you don't get access to them because they are protected by IP. So you cannot get, for example, the prefetcher model that is implemented on the latest core design for your simulator because this is not public. But we also found opportunities and positive experiences, of course. So on the technical side, we have seen there is a lot of potential for optimization in performance, in energy efficiency, and also in scientific throughput through benchmarking and co-design. We were able, in the deep projects, to tailor the system to an application portfolio, and this also allows us to have own approaches to system architecture. So we developed this MSA with this approach. One important thing we learned through this project is to understand each other's languages. So putting together application developers, system software developers, and hardware developers, these are completely different worlds, completely different scopes in our languages, and it was a good experience over the years to bring these teams together and see how they start learning, understanding each other. On the strategic or logistic side, so we saw a real impact on product development roadmap and impact on application porting and performance improvements. We have seen how codes have been developing positively over time. And we see for the future a potential for targeting something like an open source simulation framework where the community works together into the solution with open benchmark, including also up to workload mixes. So I think that's where we as a community can make a difference. To summarize, this is just one line. I hope that I could convey that benchmarking is very important in the context of co-design, that there are challenges associated to this, in particular the quantitative requirements, establishing quantitative requirements, and also measuring the real impact of this activity. But however, also opportunities on improving or applying therefore a systematic, data-driven and community effort. And with this, I thank you for your attention.
Jack Wells, NVIDIA, thank you for a very nice talk. I want to ask something else about what you learned about the particular benchmarks that you chose. Since you're working in this generalized co-design concept for a mixed workload, you can imagine that sometimes the requirements would be coherent among individual benchmarks and sometimes non-coherent, or that sometimes that the sum would be more than the parts, and other times it would be less, it would take away. So you can imagine some clustering among your benchmarks. So what have you learned about the benchmarks? When are they similar and when are they alike, not alike, and what does that mean for your system design?
That's a very difficult question to reply in general terms, so we can maybe discuss that in detail then on the break. But I don't think we were really clustering kinds of applications. Okay, it was clear when we were looking at data-intensive applications, they tend to go into one direction, and then the more high scaling, like lattice QCD, also tend to go in another direction. We have not really looked into the detail or classified in the benchmarks based on that. Then we have not done this, I think, systematically. Well, in general, what we always have to do is to find compromises. So, as you say, it's not, we were defining a system for all of them, and of course we cannot do the ideal system for each case. We have to find something that more or less fits middle well for all of them.
Yes, but as you do this as an enterprise going on into the future, how do you know if you need more benchmarks or if you could do with less benchmarks? How do you know what your coverage is of the space? It seems like this kind of analysis would help you be more efficient.
Yeah, that's true. We were always looking as a reference to the workloads of our production systems. So trying to see there what are the trends. So we see that, for example, over time, the number of AI, machine learning applications increase, and then we need more benchmarks in this direction. That's more or less, we always try to have as a reference the production machines and their workloads. Trying to look at the evolution of the last something like 5 years and try to project to the future. Of course, it's also a bit of crystal ball analysis. Yeah.
Hey, I was wondering about how application-driven this actually is and how much of it then just ends up being all CPUs. If I look back at the last 10 years of being in the trenches of co-design for DOE, right? If you ask the applications, right, they wanted CPU clusters, or they wanted whatever they were running on anyway already, right? I mean, nobody clamored for GPU systems on the application side, right? When we finally had GPU systems, none of them said, oh, we are unhappy with the NVIDIA GPUs. We really want some experimental AMD or Intel GPUs, right? Please build that for us, right? So in the end, I have the feeling that in our co-design world, at least, we designed platforms, we worked with the vendors to improve them for like kind of motives, right? And then we told the applications, now you have to adopt this.
Yes, well, that's where the factor of available technologies and cost constraints play a role. So, as much as we would have liked to fill the requirements of the applications perfectly, we have to play with the fact that if you want an exascale-based system and it's only CPUs, it's going to be extremely cost expensive in terms of the power bill, for example, or electricity bill. Yes, at the end we are forcing them in a given direction because that's what we can also afford as a computer center. That's the way life it is, unfortunately. So we try, and that's why I put there kind of the scope of our co-design. So there were things that were fixed that we cannot change. Some of them are internal to the project, some of them are technology-based. Playing with these factors is we have kind of even free parameters, and these are the ones we can tune. Yeah.
Any other question?
Hi, this is Fei Wang from Oak Ridge National Lab. So I have a question, or can you make some comments on your application selection process? So you mentioned that you have a set of like a system design criteria, like a compute intensive, communication and balancing. There are others like CPU, GPU memory ratio, etc., etc. So when you select the application, do you look at which particular system aspect that this application is trying to stress out, or do you kind of more look at if we have this application as our workload, we're going to select it nonetheless? And in some cases where one application really stress, put a strong stress on one aspect of system design, and it pretty much make the lesser demanding application almost irrelevant in terms of evaluating the system capability. So in that case, do you decide we'll have this mix nonetheless, or you want the one take over the other?
It was a bit of a compromise between both. So in particular in EPI, we definitely had a matrix of system parameters we want to stress, so memory bandwidth, core performance, and we were looking at the benchmarks and applications that stress these elements. We always, however, need also to look back into the overall application mix of an HPC center. So another thing we also were targeting to cover are different programming models. So we wanted to make sure that we have applications that use API, OpenMP, but also maybe some with OpenCL, so that we can serve all the landscape of users we have on the HPC systems. And if we found a specific application that stress a given architecture and there is another one that is stressing it but less, then maybe the other one was not selected. Cases where the code it was very, very important for the HPC portfolio, we maybe took it anyway, just to make sure that maybe there are other aspects that we need to look into. But yeah, so architecture, stressing specific architecture elements is also certainly one of the factors taken into account.
Any other question? Actually, mine has been answered already. So
Okay.
there was, indeed, on how to, when you were on slide 4, I think you mentioned the fact that you are using the current codes and knowledge to improve the usage of the HPC system, and indeed this relies on what you have today and how do you foresee what you will have. But you answered. Thank you very much.
Yeah, you try to kind of project and extrapolate as much as possible, but we always had at the end then the kind of feedback, so the final evaluation on the final system to really confirm if what we had originally expected was really manifested.
And especially also with the exascale system, I think we kind of all have that. A few years ago it was on the HPC, and now you have to do AI, you have to do data analytics.
Right.
soon we will have to do content computing, or we have to already. So yeah, how do you integrate that? Yeah, thank you very much.
Thank you.
So our next speaker is Andreas Erten from Forschungszentrum Jülich, head of Novel System Architecture Design Division and Accelerated Benchmarking.
All right. Good morning, everyone. So this is basically the complementary talk to Estela's precursor. So we're moving from processors to system design now to actual procurements. And this talk is heavily inspired of our ongoing procurement, the Jupyter procurement for the first European exascale machine, which I cannot tell you a lot about, but those things I can tell you about are in this talk, and if you want to know more, you can check me out in the break. So, in order to make sense of our design decisions and how this benchmark suite came to be, I want to quickly sketch what JSC is. So JSC is the Jülich Supercomputing Center. We operate HPC resources for our campus. So we are embedded in the campus of the research center for the state, North Rhine-Westphalia, for Germany, and for Europe. And there is different resources available for each of those categories. And of course, we also do other things, but for the resources, those are the most important points. Nearly every workload we run is based on scientific workloads or from researchers, so we only have few industrial use cases. They are possible, but just traditionally those are scarce. And every person, every researcher needs to go through a peer review process in order to get their compute time. So every use case we run is scientifically sound or has a certain use case attached to it. And I think this leads to a very heterogeneous workload. So on the right side, you see a pie chart of applications running on our systems, and the largest one is 14.8%, and all of the others are below 10% each. And you see that the majority of those are at 3 or 2% or lower. That's the others category. I might spoil that for the 15% there, that's a QCD workload, which in this time where I looked at that, just had a lot of compute. That's traditionally also the case for other years, but this year it was 15% of the compute time available. But so we are very heterogeneous. There is not one dedicated workload which takes half of the system time or something. So the largest you can get is 15%. And the categories which are hidden in here, because I cannot tell you, is physics, climate, biology, chemistry, then AI as a method, and many other things. Those are supported in our center by different support structures. So there is things, what we have, those are SDLs and HMLs. SDLs are the simulation data labs. They are the domain-centric labs where our researchers work together with the domain scientists in order to get them onto the HPC machines and improve their workload. So the interface between the HPC and the sciences. And the HMLs are orthogonal to that. They are the algorithms, tools, and method labs, where people look at it from a more HPC-centric view, basically looking on methods, like we have a HML on parallel in time integration, or I have an HML looking at GPUs, so that's basically the other point of view. We don't care about the algorithms, we don't care about the sciences, we care about the hardware in this sense. So the task for a procurement, if I may show you, or not sure. No, there is that we respect current and anticipated workloads in procurements of new systems. And Christian already mentioned how yeah, how hard this can be with respect to new systems, but we'll try our best. So we have compiled a benchmark suite, which is evaluated in different quantities, but the main assessment is the total cost of ownership. And there we rank the proposals by what I call now workload intensity. So how much workload can be run on the system over the lifespan of the system. There is also energy consumption respected in a simplified manner, because the formula is already quite complicated, and we wanted to make it a little simpler. And then we have a really large formula which calculates this value and then creates a ranking out of this to give us, for new procurements in this case, the total cost of ownership. For all applications, we needed to choose one metric, which is the metric which we quantify our workload on, and in this case it's the runtime, because it seems to be the common denominator for all of them. And this is application space. So in our TCO, total cost of ownership evaluation, this is always application based. And I'm going to talk about this in a bit. Then for the Jupyter procurement, so for the exascale procurement, we had a new idea to integrate a new facet of the system into our procurement, and that is what we call the high scaling benchmarks, where we wanted to respect the scale, the large scaleness of the system into the benchmarks, and we wanted to run certain workloads over the full size of the system. Full size is not entirely true, I'll tell you this in a second. And here the metric to compare things is the scaling efficiency. And also this category is application based. And then in the end we round this up with a set of synthetic benchmarks to test individual features of the system. So looking at the various application benchmarks, we have a central repository in the institute, which is there since 2017 around, and it contains 50 benchmarks, which are defined well defined to various degrees. So there is some which have really good quality to send them out to other people directly, but there is also some which are quite rough around the edges and need some more love. And they are maybe created for procurements, but also for other endeavors like as Stella just showed you. So this is a different repository, but of course we are in one institute and they might influence one another. All of them are well-defined, simplified versions of full-scale applications running on JSC systems. I try to skip the word mini-apps because I think that's another category of this. So those are actually reduced applications. Here we are usually running the full applications, but in a simplified manner. So sometimes we remove I/O from the timing, things like this. And we use these applications here for TCO and high scaling. And here, just for illustration purposes on the right side, I have one of the plots which we use in order to make sense of, in this case, the scaling behavior of our applications, which we also have always accommodating those applications. When we select benchmarks for procurements, we go through this set of 5 points, which I thought of because that usually happens organically. So we analyze our current system workload, then we discuss the workloads with the associated SDLs and ATMLs, and maybe further scientists, which are not necessarily from the institute, but maybe with associated universities, coming hopefully to reference applications out of this, and we analyze them, and then we sort them, or we dissect them regarding suitability. Suitability has many facets. First, I told you about simplification, like where we want to make applications a little simpler. So that doesn't work for every application. You need to be the application needs to be simplifiable. Then sometimes input data might be an issue. Like we have a weather and climate simulation which takes in multiple terabytes of input data, And this is not very handy for a procurement, so that's something we need to respect. In the end, we did choose it anyway. Then robustness. So how well does an application run if you change certain little parameters on the system, and how robust is it to fiddling by the things we don't want. And then also important for us, how is the result of the application verifiable? So how can we make sure that whatever anyone changes on the application doesn't change the outcome of the application? And then in the end, we need to also make sure that the full set of benchmarks is balanced. And I actually added one more point just a little while ago. Give me just quickly time to relaunch this, because while listening to the first talk, I added a little more to the balance of the full set. So that for sure is domains. So we've talked about the different applications which are running on our systems, but that is, they're all coming from certain domains. But then also programming models are important to us. So we see a certain cross-section of programming models used in our system, and this cross-section should be also part of the set of application benchmarks. And then the profiles of the applications, which also you had a question before too. Then when we create the benchmarks, we define the benchmark case, the execution size, so how many nodes are used, how much memory is used. It depends on the benchmark, but usually it revolves around the number of nodes used. We need to shrink or simplify the application, so we are not simplifying too many apps, but there is some level in between which we want to get. Sometimes it's necessary to convert to a reference metric, so we decided to use time as our reference metric, but there is applications, for instance, machine learning or deep learning tries to use images per second or tokens per second, and that kind of needs to be converted to a metric which is fitting to the whole process, so that's in our case time. It turns out for a lot of our benchmarks we needed to add verification, because usually it's a scientist who judges this on a turn-by-turn basis, knows how to read these things, but in a benchmark set this doesn't work. So there needs to be some means of automation. Then we analyze all of this, profile it, and create scaling plots. And for us, the last step was then to harden these things, so to look at it critically, also in a cross-review internally, and find out where things went wrong and then improve this. We call this the harden. And then I mentioned this new category of high scaling benchmarks. So the idea is that we take our current largest system, which we have on site, it's Joules Booster, and we run something on that system, and then we want to interpolate to the new the workload to the new system, weakly scaled, and we judge the quality of the run by the scaling efficiency. And actually, we don't use the full Joules Booster for this, because that's really very hard. We rather take round numbers, so we take a 50 petaflop subpartition, and we use the peak value of, so the virtual peak value of the installed devices, which here we use 50 petaflops, so then we target for our new exascale machine 1000 petaflop, so we need to scale the workload 20-fold. In order to address changing hardware devices also, so there is at least one generational change between Joules Booster and Jupyter Booster, in terms of hardware devices. We also provide 3 variants of each high scaling workload with respect to memory usage, and that's small, medium, and large. We found this actually quite a good idea, especially for a system which is the first exascale system, so it's the entry point to a new era, high scaling workloads as large as you can get, so that's really nice, but we found this really hard to do. So we invested many node hours into that, and at some point we needed to look into crystal balls to find out how this is going to look like. So we'll see how good this endeavor was, and if we succeeded when all of this went through. Yeah, let's see. So to tell you a bit more about now the Jupyter procurements, for us it's the largest procurement to date, so we have never procured such an expensive machine. We do this together with your HPC joint undertaking, who is the actual procurer of the machine, but we provide the technical support for this, or the technical expertise, and it's going to be hosted at our site. So in order to prepare our benchmark suite for Jupyter, we already started at the beginning of 2022, or maybe a bit earlier, so it's about 18 months of work for us, and there is more than 30 people involved from our whole institute, so that's about 10% of our institute. We created captains per benchmark, and that's usually one person. For other benchmarks then it's also there are co-captains, which have up to 3 people attached to benchmarks. We met every 2 weeks in these 18 months, or well, maybe for 12 months of the 18 months we met for 2 weeks to discuss the current status and see how we progress in this topic. We use issue trackers like good project managers do, and we came up with a status tracker to track the individual status of each benchmark, which contained 11 points, which are like going from the first one is the source code at all available, because sometimes people are using proprietary source code, but that's an issue. So we need to come up with a solution for that. So that's this first point, which is very simple, but it turns out that sometimes it isn't. Then the second point is something like is the input data available. Then point 4, you'll see again in a bit, is the Jupe integration done. And then the last point, so I skipped a few of course, is about the description and the documentation, which turned out was quite involved. In the end, we came up with 16 TCO application benchmarks for the benchmark suite, and of these, we also selected 5 as being the high scaling application benchmarks, and we also created a modular benchmark. So the idea that you heard already in the status talk, where there is a benchmark that runs at the same time on a Jupyter cluster and Jupyter Booster. Those were the applications which we selected for the benchmark, and all of these are highly inspired by our workload. So if you don't know them, that might be because they come from our systems. But some of them you probably know very well, so like Ember, Quantum Espresso, or macOS, or Pick on GPU, or Icon, Gromex. So there is a lot well known, but there is also some unique to Jülich. There is also 3 AI benchmarks. So there is on the right side MMO clip, NLP, and ResNet. So NLP in this case is more a direction than a benchmark, but we used a Megatron deep speed benchmark for this, inspired from one of our projects which we have, and made a benchmark out of this. Then to add to just quickly say about the synthetic benchmarks, so those are really artificial benchmarks which test specific design parameters and features of the system, like the network connectivity, the network performance, specifically looking at MPI, which is still that thing we use to communicate between nodes, I/O performance, and then looking at compute, for instance, with HBL or HPCG, or looking at memory performance, for instance, with Stream. And they are evaluated, all of them are evaluated separately and also relatively. We created a set of rules and created modification guidelines out of them in order to give for the people participating in the tender the chance to modify and get more out of applications from what we gave them. First off, benchmark needed to be executed as per the recipe which we gave at hand, and there were certain rules given how those things should be executed. And usually this meant fix a version for an application, so even if there is something newer, you cannot per default use something newer for the application because we haven't tested it, we cannot judge that very well. For certain applications, then this default was overridden, and for instance, for Chromex, we don't care. We just say, hey, use the version which you like is best for you. Then we expect a response with the execution time in order to evaluate our master formula, but we also want to see more things like strong scaling for certain applications and also log files, so we can judge a bit more how the execution went. Regarding modifications, so the workload is cannot be modified, the algorithms cannot be modified, and also the precision of execution cannot be modified. What can be modified are the dependencies, libraries, compiler options to a certain degree, directives. The programming model can be modified, and also in some rare occasions, also the programming language can be modified. But all those changes need to be documented very well, and we need to have the possibility to push them upstream. Just from a technical point, because I like this a lot, but I probably will bore you with this. Anyway, give me 1 minute. There is one GitLab repository for each of the benchmark. You saw that already, so this is the central place where we organize everything. And internally, each benchmark is structured very similarly, nearly identically. So we make use of Joop, which is our Jülich benchmarking environment, which is as good as any other benchmarking environment, but we like it and we use it a lot. And then there is a way to abstract away things from Joop scripts, which are system specific, through a file called platform XML. Basically, it contains global variables. And those were used a lot to make the benchmark system independent. So basically, by switching out platform XMLs, you can go to a different system but use the same files. We include the sources in each repository as Git submodules if possible. Each repository also contains internal data and evaluation. The description and rules and caveats are in one file, which we always call the description file. And then the key metrics, so the runtime, is in machine-readable files in there so that we can collect them through scripts. The Tenary package then is auto-generated, or semi-auto-generated from GitLab, because each benchmark then is archived to a tarball with the submodules resolved. Descriptions are converted to TeX and then assembled to a whole document and then given out. So what we give out to the participants in the tender is really the descriptions which we have in the repositories. And then we deliver this via the website with lots of checksums included to make sure that everyone who's downloading the file has the proper file and we can refer to them properly. On the right side, there is just an example how these Joop scripts can look out. If we look now, this now here is in YAML, so it's not XML, but you see the benefits here. For instance, you can use a lot of variables here. You can use parameters which are defined in the platform XML, and then they are used in pre-populated job scripts. And then you can also use tags here at the bottom, baseline and scaling, where you use different queues in this case in order for your workloads. So the next steps are still there, because despite 18 months, some things are still to do, so there is never enough time. The most important thing is that we want to set up continuous benchmarking of our benchmarks, because we have already put them well aligned into this Joop structure, so it's easy to get them into a continuous benchmarking environment, which we have set up with Jacamar already. And yeah, this should be not so hard. We are going to tackle this in the next weeks. And we plan to use this for regression testing of various things. So first the systems, then our software stack, but also then the benchmark itself. For monitoring of all of this, and also for the system bring-up. So that should hopefully play a key role in the bring-up of the Jupyter system. And then when the procurement is through and everything has calmed down a bit, we want to implement some improvements into the benchmarks and then somehow publish the work as well. Estella presented already some lessons learned, so I do this as well. So we think that large-scale systems need large-scale workloads, but the devil's in the detail, and it's really hard to prepare these things on a production system, which is basically full all the time. So yeah, that was hard. It was also time-intensive to hunt for the proper workload size. You want to be agile, so your workload shouldn't be too high, but you're procuring a large system, so it should be somewhat high. Yeah, so it's a hard task. We have many traditional HPC workloads on our system which are reasonably stable, so we can pick them up and make a benchmark out of them. Not so much for AI. AI is, your workload looks different in 2 months from now because someone found this cool new toolkit or algorithm and they implemented it and everything looks different. Verification is really hard because usually in real world the researchers know their workload and they will look at it and they will tell you, hey, this looks good. And how do you know it looks good? Yeah, well, the parameters are between A and B and not so much as C. But this needs to be automated because otherwise it cannot be verifiable by a person participating in a tender. Then there is this inherent crystal ball-ness when preparing for workloads for a machine of unknown size. So this was kind of hard for us. And then my personal beef was that even in our specific HPC niche, in our HPC block, there is corners where we still can communicate better and better understand each other because things can be lost in the translation. And scientists, HPC scientists don't think in benchmark, and we who know benchmarks don't so much think in applications. So it's sometimes there is things lost in translation and they cost a lot of time. All right. So we are eagerly awaiting that we finally can announce what Jupyter will look like. I hear that it's not too long ago now, and we hope that at some point we can share more about the details about this, and maybe we'll see us on our system when you use it. Thanks for your time. Are there any questions?
Thank you. Thanks for that overview. I was just wondering, in your total cost of ownership equation there, the idea of programmability or how much effort it takes to get an application up and running on a, let's say, esoteric type of platform, yeah. How are you thinking about that in the procurement?
It's really hard. We want to have programmability, but I don't think there is a fair metric which can judge this. I'm not sure. We haven't found one. So the solution we came up with to respect it is that we have this TCO formula, which there is a software criterion on top which can weigh this up or down. And the software criterion then allows to a certain degree based on a set of soft features to be upscaled or downscaled. And one of the soft features is programmability, but it's one of many. So there is further, I mentioned in passing that we also let us give us strong scaling values for each of the points. So we have one reference node count which goes into the formula, but the evaluation of the strong scaling goes into the soft part of the evaluation. So we call this a quantitative evaluation and a qualitative evaluation. The quantitative evaluation is through this master formula, which is heck complicated. And then there is the qualitative evaluation, which ranks this up and down to a certain degree, just a little wiggle room, regarding all those softer criteria like programmability or scaling efficiency.
Thanks for the talk. So I assume right now the Jupyter, you issue the RFP but not selecting the vendor yet?
Let's say we have, there should be an announcement about the vendor.
Okay. All right. It's not like I try to know the vendor at this point, but my point is, okay, between you issue the RFP, select the vendor, and the vendor respond with the benchmarks you outlined there and give you certain numbers. Since you asked for some execution time, etc., but you did not ask for the projection, meaning that they don't have the future hardware, but you guys have to do extrapolate to figure out, when the hardware actually arrive in 18 months or even 2 years, how much of this confidence you place on the projection either you or them gave to you. So is there a thought, a rationale behind all this? How do you?
So in the RFP, we request that the vendors show us reasonable projection to the expected hardware device, and then in the qualitative evaluation, this is then respected, how they can make sure that we trust what they project.
Okay. And earlier, I think you have a slide that talk about you use your current, the largest supercomputer, and then do the 20x projection. What's that for? Are you assuming that your current architecture and the future architecture are roughly the same?
I don't really understand what you mean, but so that is that is what behind that. So we go from a 50 petaflop machine to a 1000 petaflop machine. So we have 20 times more flops available. So we are scaling our workloads 20 times. So that's the idea behind that.
Okay, so are you saying that your current benchmark, your peak flops can reach the 50?
Yeah.
Okay.
So we have a certain set of applications which we run at 50 petaflop peak. Those are 642 nodes of Joules Booster, and those are then projected upwards to Jupyter Booster's equivalent. And just to refer to one point, so all the information which I've shown you today is after the RFI. There is no RFP information in here because RFP is still technically ongoing.
So thanks for the talk. But when you think of large supercomputing systems, and that too cost effective, GPU comes into picture. So would you mind sharing with us, like, how do you evaluate these GPUs when it comes to RFP?
So we've already made clear in our RFI that we are going to have a GPU system. So we knew from the beginning that all of our benchmarks will target GPUs.
Right, but what we see here, we don't find many applications which scale completely on multiple higher number of GPUs. But when you think of that kind of system where multiple GPUs plays into picture, so what applications, how do you select the applications which will make you get there?
Yeah, that was really hard. So we've, out of our 14 benchmarks, we were able to select 5, which we found had reasonable quality and could show scaling on the 15 petaflops and promise scaling to the 1000 petaflop. It was really hard, and we needed to come up with a lot of workload interpolation or extrapolation and look into the crystal ball how this is going to work, because we don't have any means to test this. Right? So there is no 1000 petaflop system at our disposal where we could test this.
Yeah. Thank you.
Okay, thank you very much.
I think Fabio and
I think we should stop. You can ask the question during the break. Thank you very much.
It's not my fault. Next he doesn't hear me.
Yeah, I can hear you. Okay, so I go to the presentation.
Okay.
Thank you very much.
Okay. Is everything working?
Yes, we hear you perfectly well.
Okay. Thank you. Good morning. Thanks for the invitation, and I'm sorry I couldn't be there in person. And yeah, thanks to the organizers for accommodating this remote presentation request. So my name is Sanathanam, and at Bristol as Director of Advanced Computing since late last year, so fairly new. So a little bit about Bristol, if you don't know. It was not, it was fairly decent university from the UK standards or European standards, but it's got very much research oriented, and it has some leading projects. So the pictures I put in there is one from Banksy. He's from here, so you can still see some of his murals there. And the other thing I think in our community Bristol is probably known for is there's a BART system which is led by Simon McIntosh-Smith on ARM-based technologies. So since I'm here only for less than a year, so the work is being largely done before my time, and we are building on it. So the main work, body of work I will present is within this solution called cluster in the cloud, and then it's been extended for on-premises system for infrastructure as code, and the infrastructure we are using is funded through EPSRC equipment funding. So for those of you who have looked at, various things about infrastructure as code, some of this type of pictures come up quite often, and there are so many of them. So I put the link in there. So it's like often call it is pet versus cat model, and more often than not is presented in the context of individual servers or services. In this talk, I will present it in the context of an HPC system or a supercomputing platform. And how and why then it changes the way we do it, as the title of my slide. It's more sort of a mindset. It doesn't mean that we no longer do high performance computing or supercomputing. So what is different when we go to this mindset, and why there is confusion, and why we need technologies like clustering the cloud? So what you see here is, of course, Frontier. I said, okay, pick up the most famous system here, and of course Oak Ridge is part of ADAC, or a founding member. So this is a system that is built with specification to the absolute performance, and it has, from all purposes, if you look in the middle part, a stack that is vertically integrated. So if we start from the bottom, you have a resource plane where the management and provisioning infrastructure for computing, networking, and storage is there. Then the system or the cluster-specific configuration comes in where we decide on the operating system drivers related. In this system, of course, we have GPUs and a proprietary network, so those are there. On top of that, the platform layer comes in. And typically in platform, it's not that clear-cut, but we define specific systems like resource management, such as Slurm. And then we have our user software stack that user use, that could include programming, that would include optimized applications, and so on. And if we then go and move on to map it onto a more cloud lingo or terminology, we see it infrastructure as a service, platform as a service, and a software as a service. The reason it's so confusing because in a classic HPC environment, we do not look them as individual components that can be composed sort of separately, but they are largely vertically integrated. If you go to the cloud world, what is happening for a long time now, okay. is that this idea of automating this deployment provisioning of different stack, specifically in infrastructure and hardware level, through different tooling. And if you look at this picture, we can see that there is not one tool, and people use a combination or mix and match depending on their needs, depending on the experience of the team, etc. So one of the pictures I picked up here in this presentation, you can see there are tools that maybe if you have a data center you are using internally, or maybe if you have even a software stack, you may be using some of these provisioning and installation on a public cloud environment. And it goes from infrastructure templating to managing them, installing application and configuring. And there is an overlap. In cluster in the cloud, there are two of these tools that are largely used. Ansible, which is a tool for software provisioning and configuration management called Playbook. Chef is not used in that, but the reason I put it in there is the term recipes came from that. It's an automation platform. And Terraform is another big tool that is largely used for cloud or infrastructure provisioning that is used in cluster in the cloud. So what ends up then changing is then, if again we look at classic environment, then you have directly integrated Frontier, or in Europe we have Lumi environment. The hardware is the same, but the configuration will be slightly different. To a model where University of Bristol, so UOB is University of Bristol, we could have a high-performance University of Bristol cluster deployed with a recipe, a high-throughput cluster deployed a recipe, or a PI who has some specific requirements for some trusted research environment, that they need some kind of compliance and security and access control. They could be deployed separately. And there could be a pharma project, there could be industrial partners there that they would like to deploy on-prem in a very specific way, where they cannot share the configuration of a large-scale environment such as Frontier and Lumi. So that was kind of the idea of doing this model. And then it kind of disassociate or decouple it from a given hardware deployment or configuration. So it doesn't mean now there are discrete clusters deployed, but these are rather configuration of clusters deployed. So all this sounds very good, but what happens behind the scene and why the cluster in the cloud came about is important to learn. So cloud could be faster in terms of at a small scale accessing resources and provisioning them. But if a researcher is coming from a Slurm background, and as a user, they can't use it straight away. We will see a little bit of detail what cluster in the cloud does, and some of the tools are coming to bridge that gap. But when cluster in the cloud started, the idea was how can users go and sort of get the same experience as an on-demand HPC cluster, which is similar to their on-prem departmental cluster or university cluster, without needing to become experts in system administration and management. So from a user perspective, they have exactly the same experience. They go and log into a node, they submit job, compile, so they have a similar environment. They don't even know where the resources are provisioned. That was the idea for cluster in the cloud. And then it starts for them behaving like an on-prem compute cluster. And in the back end, this is one of the distinguished features of cluster in the cloud. It has this elasticity, because if you provision a resource in public cloud, they keep getting charged, unlike on-prem where the resource is there. So you need to make sure, depending on the payload of the cluster, you expand it or reduce it, because you reduce it to a point where you just keep the storage and the login and necessary nodes and do that. So this was another feature added in cluster in the cloud to not become on-demand and elastic and to control the cost. So at a very high level, this is how it goes from a user perspective. User gets access to a cluster that is in the cloud, and in the back end, the recipes can run on Oracle Cloud infrastructure, Google Cloud, AWS, and I think also this one. The project I started here doing, because I come from more an infrastructure background from National Supercomputing Center, I said, okay, this environment, if we expose the infrastructure in a way that is somewhat Terraform compliant, then it could work on-prem without a problem. And that's where we started with this thing. So there is a OpenStack cluster we built, and I'm not including the implementation detail, but the thing is, this OpenStack cluster is built with a configuration called scientific OpenStack, where it delivers close to metal performance. And the collaborator we are working with is called Stack HPC, and I put their website there, and they have since I think 2016 or 17 being specialized in delivering, and they deliver one of the largest clusters and more bespoke clusters across different countries. So they are based in Bristol, so that is very convenient. And so we started collaborating with them, and then we are using and deploying this thing. The other thing that was very important for the work we were doing is we wanted to have an open source and open standard approach, because working on backends of public cloud, that has always been, as you can imagine, a challenge that, okay, sometimes the APIs may remain the same, but the logic and other concepts. So we didn't want a lock-in side. And on the left side, what use cases we consider, so not only users can log in and submit job, but they can run other services for workflows such as Jupyter and more secure environment. So in a nutshell, if you look at it, what does cluster in the cloud do? As I said, Terraform, which is an infrastructure as a tool, creates networking, shared file system, and management. So we create an infrastructure, and Ansible configures how that infrastructure is presented, and then the skeletons are created for different and more often than not, there are only a few hundred lines of code written from scratch for each and every backend of an environment. So, and there are more optimization done, so some of these installer can do one-click environment. So this is a simple workflow where there are some common parts, and then there are some back-end specific parts. So what I didn't include here in this picture is, this is from my ISE presentation in May. Now there is not an installer, but a back-end for OpenStack. So you can see in 4 steps, you can deploy a cluster on any environment that supports Terraform backend, from setting up infrastructure to creating on infrastructure as a code compliant environment, configuring it in terms of who can access LDAP, Slurm, and verify the cluster is running, and giving access to the end users. If anyone is asking questions, they have to speak up, because I can't see anything from here. So what happened was that when this was initially introduced 4 or 5 years ago on the public cloud, it was more than accessing a cluster. Is there a question? Okay. It was really a paradigm shift from a researcher point of view. So now suddenly they were thinking, they had a situation where back in 15, 20 years, they had like these, they still do it, workstation that a group or a department would manage. They have it, but it is elastic, and they can reuse this configuration for different environments. And so they started having this sense of, I mean, again, I will go to the concept of pet versus cattle, because when I look at larger high-end clusters, which or classic HPC systems, the PET approach comes from the local team. They manage, they configure, and they operate it locally and update it. But in this case, a researcher has their own personal PET cluster, which is not then a physical environment, but is rather a recipe. And they can perform their experiment in a familiar environment, and then instead of, and that's kind of probably more important for them, instead of being in a job where they share queue with people from different domain departments, use cases, there is a smaller group that is, queuing job in their own environment and resources. And they can do, because we could distinguish this infrastructure, platform, and software as a service layer, the program, other configuration can be easily customized as per a given environment. So that exposes was almost like a revolutionary point of view in the sense of that for workflows specifically, you could stitch together environment, not only you thinking of it as an on-demand Slurm batch cluster in the sky, but more I could concatenate data analysis, interactive computing using Jupyter Hub in the form of workflows. So what we did in parallel was that we started co-designing and co-developing this thing for workflows. So here is a layered approach we are using to get there. So and on the left side you have the driver use cases from life sciences to a classic HPC and a more shared platform, and then platform with totally customized software stack. So if you look at the lower layer 0, which is a software-defined multi-tenanted infrastructure, it could be public cloud or it could be a supercomputing environment. The layer that comes above that is orchestration layer and infrastructure as a core layer, where you could have backend written in a Terraform compliant manner, or you could have Kubernetes orchestrated platform, especially if you are running workflows. Then you start thinking of digital benches and digital platform, and in this case we can use cluster in the cloud or Jupyter Hub, or there is something Stack HPC is developing which we are looking at called Asima. And finally, from a scientist or research point of view, you are composing your digital experiments for workflow, where part of it could be an HPC job, part of it could be interactive, or part of it could be your own defined software stack. As you could imagine, when some of these concepts are presented, the question of access and security comes, and this is how we are approaching it. So from a user ease or access point of view, we treat it like a single sign-on access. So there is a front door. It's not totally open. So you need to, a user or a service needs to identify, authenticate and authorize it. But within that multi-tenanted environment, you can set up some persistent labs or clusters, or you could have some on-demand for teaching, for instance, and clusters. And all the modern the cloud identity and access management controls are heavily exploited in this environment to maintain access and security concerns. So essentially, one of my colleagues said, it's like a chemistry experiment, a chemistry lab. If it blows up, it doesn't bring the whole university down. While in a big supercomputing shared environment, if a shared resource is abused or misused or has an issue, it changes the experience for each and every user. And then we are looking at it, this Azimuth is a self-service portal from OpenStack, and it is starting as a secure, automated way of accessing longer-lived cloud resources. So very quickly, in the interest of time, where we are. So everything is there. Sorry. We have the system installed, OpenStack, everything role-based for admin tenant, and we are having, I call it ongoing negotiation with the IT security council. So the infrastructure is there, provisioned in this multi-tenanted way. Cluster in the cloud has been porting to OpenStack, and we have spun up the cluster using the OpenStack MPI. We have ran jobs on these OpenStack, spun them up and down based on demand. There are still things to do because as we were doing this thing, we realized that cluster in the cloud now need a proper API server and an API access gateway if we want to make it available to larger group working on OpenStack. So this is ongoing work. And then we are doing some of the benchmarking to see if because the cluster has both, of course, GPUs and networking components. So when we are doing these software-defined partitioning or multi-tenancy or virtualization, how much, and everything is done with the pass-through, what are the overheads in terms of getting there. This part is by far the most demanding, but a great progress. And here I am leveraging the work I have been doing at the Swiss National Supercomputing Center as part of different European projects. It's called Identity and Access Management. So we are leveraging MyAccessID that was developed as part of Lumi project and Phoenix, and this I put the link and in terms of user and access management, because it all sounds very nice, it would work, but how we will then do user, project, and resource management. So these are the tools we are leveraging. How we deploy a local LDAP. We are, as I said, ongoing negotiations with the university IT services because they are quite concerned how if you get this high-level privileged federated access, what will happen. So this is ongoing work. Whenever a cloud technology is introduced, I think this is what is where you end up spending most of your time and resources. Here also, very quickly, we are focusing a lot on a consistent user experience using on-premise and off-premises resources. So there were some, Bristol has an ongoing collaboration with Oracle, so we, as a part of continuation of that work, we said how a user can go in and use a cluster in the cloud recipe to deploy it both on-site and off-prem. So this is the work we are doing, and here we are leveraging a tool called Vaulter, which is the engine for Euro HPC Lumi user and project control system. So we present this as a single pane of glass, because the idea is we want as much as possible a self-service approach for researchers in there. And if I can show it graphically in the interest in time, so we are trying to create this. So this was like a proof of concept done with the Vaulter team, which is based in Estonia. So users will go in and they can use Bristol or MyAccessID. They see what resources in the cluster in the cloud are available, and then they use this secure gateway implemented through Azimuth and can deploy the cluster, either resources on OCI or resources on OpenStack. And these are sort of the pet and kettle combined concept. So it is a pet in the sense that it's specific to a use case, but it is in the sense can be deployed on any environment usually. And that's it. So I managed to finish hopefully.
Thank you, Salah. Do you still hear us?
Yeah, I can hear you. Yeah.
Okay. Do you? I know you have to leave at 11:30 sharp.
Mm-hmm.
So 10 minutes. What I can propose, because you open very important topics such as the security need, how do you benchmark also all this virtualization part and so on. So that's really something to be discussed. Considering your schedule, what I can propose is that I can collect any question, and we can deal with that. And anyway, I have a bigger plan at the end of the day that I can share with you, of course.
Okay, that would be, and I can send you the slide deck.
Yes, absolutely.
Yeah. Sorry about this, Ms. Dana. Yeah, I would be happy to join, but I don't know when is your session. Yeah.
That will be, I will send you that. I think that will be around 5 p.m. That's the open discussion at the end of the day.
Okay, okay. Yeah, please do. All right.
Perfect.
Thank you.
Thank you, Sadat. Thank you very much. So sorry for the no question session, but compensation, this is the coffee break session.
So our next speaker is Miwako Tsuji from Recon and CCS. And she will talk about compiler and system software feasibility study and benchmark for the next generation supercomputer. Thank you.
Thank you. I'm Miwako Tsuji from Recon, and I also work as an associate director on HPC user group. So before starting my work, I'd like to announce our workshop next year in Japan, international workshop on ARM-based HPC, practice and experience. So, this covers a very wide range of the topics regarding ARM HPC. So, if you are interested in, please access this website or Google with IWA HPCE 2024. So anyway, let's start. So this talk I will introduce the feasibility study for the next generation supercomputer and some of the benchmark activity which has been done during the development of Fugaku and ongoing work. So first, feasibility study for the next generation supercomputer is conducted from last August. So this is anticipating the work to develop the next Fugaku supercomputer. So this project will qualify the needs of the computer resources for the research and development infrastructure in various fields of science and technology and social infrastructure to enhance industrial competitiveness and disappear prevention and SDG. So, and also, we try to support the data-driven science based on the huge amount of a variety of data, including simulation and AI. And third purpose is facilitate computing infrastructure that can execute entire workflow by using a wide range of computation methods or computation resources from data center to edge computer and, of course, HPC. So we have 4 teams of the feasibility study. So one is a system research and study team conducted by RIKEN, our institute. And the other one is also a system research and study team conducted by Kobe University. And third one is a new computation principal research study team conducted by Keio University. So basically, the new computation principal means quantum computing. So it means that this team investigates quantum and HPC. The third one is operation by University of Tokyo. So in weekend, so we conduct a feasibility study of the system and research and system research and study. So we have 3 teams. So one is architectural research team. So it investigates the technological possibility of the next generation supercomputer. And the second one is system software and library, which I will focus on this talk. The third one is application. So they provide benchmark set to evaluate multiple architectural choices and also system software. And this is a schedule of this feasibility study. So we are now in here in this phase. So that it means that for the system software research, we are now identifying the requirement of software development. I'm not sure this schedule is still feasible right now. But anyway, so the system software and library research group aims to study technical trend an ecosystem of system software. So we identify which system software to be developed in Japan or through the international collaboration and cost of development. And actually, we are also investigating the current usage status in Fugaku and other Japanese supercomputer, and existing system software, existing system ecosystem surrounding candidate architecture. And then we would like to define a roadmap for the next generation systems. So this is an organization of our research group. And so this talk especially focus on the compiled programming model team leaded by this written RCCS. So this subworking group, compile and programming model subworking group, focused on the compiler and programming model to understand the need and trend of application development in terms of programming language and existing code generation techniques, so including open source compilers and other programming frameworks such as the performance portability programming model. And additionally, we will investigate profiler, debugger, and so on. So, first, I will briefly introduce our result of the survey for application developers in our application research team. So, we asked 13 application developers in our application group. So, there are very wide range of researchers, such as physics, biology, life science, nanoscience, industrial application, and so on. So basically, they are expert user of Fugaku or other supercomputer in Japan. So they're not students. It means that the average age of our application developer is older than general application developers in Japan. So first, I will introduce the programming language used in Japanese community. So, of course, Fortran is always based in Japanese HPC community, so we still working on Fortran. And then Python is the second version. It is very surprising, so it is a very drastic change during 10 years from K to Fugaku. But important point is that there's only one user who uses only Python. Most of the application developers use Python and C, or Python and C++, or Python, Fortran, and so on. So, and the second part is C, and then C++, and so on. So, second part is programming for accelerators, and performance portable programming models such as SQL, COCOS, and so on. So we asked developers, so do you have any experiments for the accelerator? 12, almost 30 researchers and 30 years. So for the detailed breakdown, 11 researchers with GPU, and one answered, yes, I have used cell. And unfortunately, more than around 70% Japanese application developer answered, no, I never use or almost never use the accelerator. And I have also asked them to the experiment using performance portable programming models such as SQL and COCOS. Only one say, yes, I have. And there are some researchers who never use it but are very interested in it. And half of them never use, but would like to try if the porting cost is not so large. So it means that from the viewpoint of accelerator, so it's expense of accelerator programming in our respondent. Because actually, so our respondent is mainly from users of Fugaku and K computer. So it means that if we ask more large, if you ask many people, and then maybe the result will be changed. And they are very positive for new programming model and new architectures if the coding cost is trivial. So about benchmarking compiler. So first I'd like to introduce our activity with University of Kyoto to evaluate the compiler for Fugaku during the development of Fugaku. And then I will talk about our ongoing work to evaluate the source and proprietary compilers using feasibility study benchmark candidates. So during the development of Fugaku, we have conducting collaborative research with the University of Kyoto. So the research is focused on the wide frame simulated usage and code generated by compiler for such kind of simulated architecture. So we use code called PIC, particle in cell simulation. And we evaluate a series of compiler budgets during the development of code, which is provided by Fujitsu. And then after our analyzation, we will provide feedback to Fujitsu team. So the basic idea is we have compared the instructions, assembly instructions generated by developing compiler and ideal hand coding for kernel and Intel compiler for night running. So we checked vectorization, instruction scheduling, and speed register allocation for these three different compilers. So this is an example of our compiler evaluation using PIC code. So, this and two number means year of our evaluation, a version of the development compiler, and this two number means a month. So it means that if 1912 is December 2091, provided at December 1921, and after 6 years, after 6 months, Fujitsu provide different version and so on. So HC is hand coding, ideal code, and this is a code for internet running. So this shows the number of instructions, different instructions in this kernel. So this is a total number of instructions. Row means that row total number of instructions, and this normalization is the instruction number of instructions normalized considering the different architecture of Intel and and this is ideal number of the instructions. So actually, during the development, according to this evaluation, the number of instructions generated by developing compiler is a bit more than the handwriting code. But actually, this figure is start from 2019, but we start work 2015 or something. So it means that it is already improved. So at the beginning, there are more instructions, but according to our instruction between Fujitsu compiler team and our collaboration team, the number of instructions are developed gradually, and then now we are to relatively good number of instructions. So this is another example of the usage of the register allocation. So in case of A626, we have 32 vector registers. So according to the analyzation, developing compiler by Fujitsu use two more local registers. And consequently, two vector constant variables are created by loop instructions in the iteration. So that's why Fujitsu compiler require more number of registers which may result in high register pressure. So this kind of feedback provided to the compiler team to improve the compiler. So then it moves our preliminary performance evaluation of open source and proprietary compilers for the feasibility study benchmark candidate. So this is ongoing work, so that the result is not completed. But anyway, so So these days, open source compilers are very important. So even vendors try to move their own proprietary compiler to open source compiler. So that's why we compare the code generation of the open source compiler and proprietary compiler. So here we use Fujitsu compiler and GCC 12 and LLVM 15. So GCC and LLVM, so we may have more latest version, but these two are now currently officially supported by SPAC framework on Kugaku. So our feasibility study benchmark, there are 12 applications and kernels provided by application research team. And we will select 5 or 6 filtered applications. So for this of them, we are planning to count the instructions by using path. So we have not completed all the benchmark study, but I will introduce some of the results. So this is an example of the feasibility study applications provided by application team. So let's do this. As you can see, so we still have many Fortran applications here. Again, so another first example, I will introduce the QCD application written in C++ and ACLE. So ACLE is an intrinsic language defined by ARM. So it means that if everything goes well, then the number of instructions is not so different between different compilers because it uses intrinsic. So first, I will introduce the result of the different compilers. So as we expected, so the number of instructions or number of floating point operations are almost same in all these 3 compilers because it uses the intrinsic. But interestingly, LLVM generates more number of the row post-draw instruction, which may suggest that there are several spills. And this is a detailed breakdown. This is a kernel. This is the number of instructions for a specific kernel called BDD in S. And as you can see, this kernel is almost completely written in ACLE. The number of instructions in Fujitsu compiler, number of the floating point vector instructions by all compilers are completely the same. So, the number of the floating point vector instructions of 3 compilers are completely the same. But actually, Fujitsu and GCC GNU compiler generates almost same number of instructions in different categories. Of course, the instruction schedule will be different, but the number of instructions, from the viewpoint of the number of instructions, they provide a similar assembly code. So it is surprising. But in case of LLVM, there are several redundant instructions. In some sense, it's redundant instruction. So it suggests that LLVM may generate kind of the redundant instructions for the address computations or something. So this is another example. So I will skip the details. So this code is mainly written in Fortran. And in this case, different from the previous case, the number of instructions are very different from the Fujitsu and GNU compiler. So because Fujitsu team is originally very good for the Fortran compiler, so they have a very long tradition and very good team to provide Fortran compiler. So that's why open source compiler is still behind the proprietary compiler. So which means that this result suggests that for the Fortran compiler, we need more effort to improve the code generated by open source compiler. So especially the execution time of this constant is 8 times longer than the Fujitsu compiler. And this is another example, also written in Fortran. So in this case, for both, surprisingly, for the both source code, proprietary or Fujitsu or GNU compiler, they do not provide a good vectorization in this code. So very low vectorization percentage in both cases. So surprisingly, GNU compiler, from the viewpoint of the speed, GNU compiler is better than Fujitsu compiler because the number of effective instructions is less than the Fujitsu compiler. And as you can see, there are more store register, there are more store instructions for store registers in case of Fujitsu compiler. And also, there are more load floating point scalar instruction in Fujitsu compiler, which also suggests a kind of speeds or the scalar values. So, in summary, we are now doing the performance comparison between open source and proprietary compiler. Actually, we have 12 applications, but I'm still working on the 5 or 6 applications, and I only show the 3 examples. And actually, from my viewpoint, open source compiler are now continue to evolving, but we may need still need for there are several rooms for the improvement. So in this talk, I will introduce our feasibility study for the next generation supercomputer. Especially, I will introduce our benchmark activity for compilers. So during the development of Fugaku, we have evaluated compiler using PIC application and contributes the performance improvement of the compiler. And also, we are now doing performance evaluation of open source and proprietary compiler using the feasibility study benchmark candidates. So, benchmarking for system compiler, system software and compiler for code design is a very good activity because system software can be improved even after we fix the hardware. So after we define the hardware or microarchitecture, it's difficult to change because the cost is heavy. So for future work in our feasibility study team for the next generation supercomputer, so we try to evaluate the performance of portable programming model from the viewpoint of instruction and also porting cost. Because many application developers are very interested in the porting cost, and if porting cost is low, they may try to use a performance portable programming model, but if not, maybe they deny. And also, we have to consider how to benchmark Python applications or Python compiler itself. Actually, it is just my opinion, but Python itself is an application. It is not compiler because it is also it is a kind of a runtime application which executes different kind of application. So it is a kind of meta application from my viewpoint, and I have not any idea about how to benchmark Python itself, especially C Python. So that's all. Thank you.
You have any question for Marco?
Thank you very much for the nice talk. Just a curiosity, so you have made a nice evaluation of different compilers and you find differences on number of instructions and so on between them. When you give this information back to the compiler developers, what happens then? Yes. So what is then the consequence, or what is the next step?
What's the next step? So far, actually, Actually, the main reason that I'm doing this comparison is that many vendors try to use open source compilers. So, in some sense, if the result of open source compiler is really good, then we can give kind of the verification or support to their movement from proprietary compiler to open source. But actually, for some application, we need more, open source compiler need more effort to achieve a specific vendor compiler tuned for the specific application. But on average, I think it's will be very good.
Thank you, Minoko. Okay, so thank you very much, Minoko.
Thank you very much.
So this concludes the first part of this day, which was somehow a perspective of the, let's say, system community, sysadmin. So as you see, the idea today is that we have somehow three communities showing their point of view on the benchmark, how do you use it, and what for. So then we have the application community. Just one point, the lunch will be at 1 p.m., right? 1 p.m.? Yeah, because you had food already 10 minutes ago. So just to I plan an open discussion that we can have this afternoon. So maybe what was interesting this morning, we had a really different approach. From Yurish, you have a very two different approach. The cloud aspect also is really interesting. How do you benchmark also on this kind of infrastructure? I will present you that tonight, hopefully if we still have time. The idea is that if you wish, we could all work together to a white paper, making a white paper on all these different perspectives. And there was something interesting that you presented in your presentation, Estela. At some point you mentioned, you know, the lifetime of a benchmark. And that's something really interesting, because you'll see that later. At the beginning, indeed, you extract something from a scientific application. The scientific application evolves, and how do you make sure that actually the work you are doing is still scientifically alive and has a sense? So yeah, the idea is to bring everyone around the table and somehow make sure that all the work we are all doing, sometimes together, sometimes not, benefits for everyone. So at the end of the day, maybe having this discussion on possibly metadata to characterize what is a benchmark, and for example to characterize the lifetime of an application, just make sure that your benchmarking has still a scientific meaning in the scientific application, maybe a metadata, we say scientific tools for C. Is it still alive actually in the scientific application or not? So never mind, we'll address that tonight with the several point of view. So our next speaker is Cohen de Graaf from University Rovira et Virginie. Normally.
Okay. Welcome. So this is from a applications perspective, and I want to tell a little bit of our experiences on somewhat large-scale computers with the electronic structure program Chrono, which is a massively parallel and GPU accelerated program for a non-orthogonal configuration interaction. Just to very shortly introduce electronic structure calculations, everything in that aspect started in the beginning of the 20th century, in the 20s, when there was the quantum mechanical description of the chemical bond in H2, the simplest molecule that you can imagine, proposed by Heather in London. They proposed a wave function to describe the bond formed by the electrons to hold the two nuclei together of two hydrogen atoms. This very simple wave function evolved into valence bond theory, where you have, and that's important for our electronic structure program, where you have non-orthogonal functions that describe each of the two electrons in the system. This valence bond theory stays very close to Lewis structures, which is basic for all chemists to describe chemical bonds, but it is computationally very elaborated. I mean, this very simple wave function that's very easy to treat, that you can do on a piece of paper, but as soon as you deal with 100 or hundreds of electrons, the non-orthogonality becomes a bit of a problem. At the same time, almost at the same time, there was an alternative theory which uses orthogonal orbitals. And this should be a marker. There was an alternative theory introduced by Hund and Mulliken based on orthogonal delocalized orbitals. And this theory is computationally very advantageous. It is now used almost in 99% of the applications of electronic structure theory, but the problem is that it's much less intuitive. There is no direct connection to the way chemists think about chemical bonds. So a few years ago, there has been a renewed interest in non-orthogonal wave function based methods, and I will discuss a little bit our implementation of a electronic structure theory based where there is no restriction on the orthogonality of the orbitals. So we use non-orthogonal orbitals. The advantage is that we have full orbital relaxation. In our implementation we have a full description of all the electron correlation, and the most important thing in this aspect is that we have very short wave functions, which allows for a very intuitive interpretation. So these are like the advantages. So we have a very accurate description of the electronic structure. We do have an intuitive interpretation, but it's computationally very demanding. Before going into how we use it on big computer systems, I would like to take you step by step through our non-orthogonal CI approach. These are systems that we typically take a look at: organic crystals, charge transfer salts, donor-acceptor complexes, and many more. These are just three of the examples. And our computational procedure is step by step is in the first we calculate accurate wave functions on each of the fragments that we have in our system. So for example here we calculate some electronic states on fragment A and on fragment B. These can be the same, they can be different, they can be connected. And we calculate, for example, the lowest, the ground state of the system, a triplet state, some excited singlet states, cationic, anionic states. And we do that separately so that we have full orbital relaxation and a complete static correlation. And then in the second step, we construct multi-electronic basis functions, which we call MEBFs, by combining the wave functions that we have calculated in step 1, by combining them to make wave functions of the ensemble that we are looking at. In this case, AB, can be ABC, can be larger ensembles. So we combine this, so we make one basis function, multi-electronic basis function, by combining the ground states on the two fragments. We do the same for a local excitation on fragment B, in this case, combined with the ground state on A. The other way around, a local excitation on A combined with the ground state on B, a double triplet state, and so on and so on. So we also construct, for example, here are charge transfer states in which one electron has moved from fragment A to fragment B, or the other way around. What do we have now? We have now a diabatic description of the states, which are completely recognizable, which is not the case when you use standard orthogonal approaches. We have full orbital relaxation, but they are non-orthogonal. The calculation of non-orthogonal matrix elements, like these, where this is the Hamiltonian of the system, requires a lot of work, but it can be done in a very efficient way with what we call the GNOME algorithm, the general non-orthogonal matrix elements, which has been developed in Groningen in the Netherlands in the early 80s. At this time it was not possible to do very big systems, just very small model systems, because each of these requires a singular value decomposition, a symmetric eigenvalue problem, and processing a long list of integrals. And these are the ingredients of the calculation of all these matrix elements. Once you have calculated all the non-orthogonal matrix elements, you can now extract information from the matrix that you make with these matrix elements, the non-orthogonal CI matrix. You can calculate electronic couplings between initial final states, which is very interesting for to study many physical processes. And by diagonalizing this, by solving this eigenvalue problem, you get the final wave functions and the energies. And the advantage is that since this matrix is very small, it's typically below 10 or well, let's say 10, of the order of 10 by 10. The wave function is very, very compact, but since these MEBFs are of such high quality, the wave function in itself is very accurate. And since it is so small and so easily recognizable, it's very easy to put very nice labels on each of these configurations. You have a very easy way to interpret your result in terms of physical concepts. This NOCIF is implemented in Groninger, as I said before. It's an open source program. It's on GitLab. We have a web page. As I said before, it's massively parallel. It's GPU accelerated open source. It is, of course, under constant development. Our latest release is of July this year. And for the calculation of these fragment states, it's interfaced to open source program, standard quantum chemistry code, and we work a lot with Monkas, with Open Monkas. So let's go now in a little bit into detail why it is so much work that we have to do and why it is so parallelizable. If we take a look at this matrix element, for example, this wave function, this S0 fragment state, can be of the order of a expansion in 20 determinants typically. That's a very small expansion, but for the example, it is a nice illustration. So one fragment state, a ground state on one of the fragments, 20 determinants. Then if we make the MEBF, so by combining the two ground states on the two fragments, the wave function becomes already 20 times 20, 400 determinants. So now we have already 400 determinants, and then to evaluate this matrix element, We have 200 determinants here, we have 200 determinants here, and none of them can be discarded beforehand because of the non-orthogonality of the orbitals. And so we need to evaluate like 160,000 determinant pair contributions to calculate this one single matrix element. That means that we have to do 160,000 SVDs. We have to solve 160,000 eigenvalue problems, and we have to process the integrals, the 2 electron integrals, 160,000 times. That's of course a lot of work, but it's fully parallelizable. And we have fully parallelized it. Open source, that I already said, Chrono is Fortran 90. It uses OpenMPI or any other dialect of MPI that is implemented on different supercomputers. And for GPU offloading, we use OpenACC or OpenMP. How does the distribution of the different nodes work? We have a master worker setup and a model, and in the setup phase, the master generates the list of determinant pairs. So this list of 160,000 determinant pairs. And at the same time, all the workers receive the 1 and 2 electron integrals and all the orbital coefficients, and they reside on the GPUs, on the workers. Normally these are the GPUs. During the whole calculation, there's no data movement anymore. So then, when the setup phase has been done, so all the GPUs have the integrals and the coefficients, the master has the list of determinant pairs, then the master starts broadcasting 2 integers to each of the workers. And it says to worker 1, you work on the first 32 determinant contributions, determinant pairs. So it only broadcasts 2 integers, and then the worker 1 starts to calculate the 32 first contributions to the matrix elements that we are working on. Worker 2 does the next 32, and so forth and so forth. So in the beginning, the master is only broadcasting 2 integers and start waiting to receive the results. So then at a certain time, worker 2 is a very hard worker, finished its 32 contributions, and it sends back the results, which is where the master receives only 2 integers, so which contributions it had worked on, and the 2 reals, which are the contributions to the matrix element. Immediately, the master saves these 2 reals, and it sends back 2 integers and says to worker contributions to the matrix element. And that goes on, then worker 1 and worker 4 are ready. The master accumulates the new contributions and sends back 2 new integers to these workers that are waiting for a new task. Now on very big machines with a lot of nodes and lots of GPUs, etc., the number of processes can easily become I think we are almost now, we can easily generate 500,000 ranks that we are working on or more. And then it can happen that the master becomes flooded in receiving messages and sending it out. So we are now working, we have recently implemented a layer in between the master and the workers, which I called here submasters. And now the master hands out larger tasks, and the submaster hands out the smaller tasks. And this avoids that that the master gets flooded. So this is very efficient way of parallelizing. For the GPU offloading, we do all the SVD and all the eigensolvers, and actually also the integral processing. We do everything on the GPU. We ignore actually all the CPUs that are, the CPU doesn't do anything actually. eigensolvers, there is internal in Chrono, there is ISPAC results, routines, and we can use MKL. For NVIDIA GPUs, we use QSolver or QSolver J, the Jacobi version of the eigensolver. And on the frontier, which has AMD GPUs, we use HipSolver and ROCsolver, but there's still a bit of a problem with the library there. To implement it, we have written interfaces from Fortran to C to use these QSolvers. This is a typical interface for QSolver J. And the offloading in the code goes like this. So if we are using QSolver J, we set some things. Then if we use OpenACC, we use these commands to initialize the GPU. And if it's OpenMP targeting, then we have these directives in the codes. This is the call to the QSolver. And here is the handling afterwards, and this is the call. These are a few other calls that we would do. So that is for the eigensolvers. Processing of the two electron integrals, that's another big chunk of computational resources that we are using, and that is mostly in a similar way, where we can either use OpenACC or OpenMP targeting. We have here two versions of OpenMP, because some of these commands were incompatible with different versions of OpenMP. Now we come to scaling. So how does this perform? These are some of the performance, the benchmarks that we have performed for. First one on Summit for these two fragments, which are not small systems. I don't know any other non-orthogonal based code that can do these big molecules. And here you see the scaling, and you see that we scale ideally up to the limit of the machine. The machine now has 4,600. In the time that we did this benchmark, I think it didn't yet have these 600 extra. But we scale linearly up to the machine limit. For the GPU acceleration, we could not, of course, do this, because this, if you do not use GPU, that takes forever. If you do that only on CPU, so this is a slightly smaller system. And here you see that we have quite a large GPU speed up to 60, a factor of 16. That's on Summit. We also have installed the code on Jules Booster. On Jules Booster, you also see a complete linear scaling. We were only allowed to do 512 nodes. I think it was already an exception, because the normal limit for users was 384, I think. Anyway, we got it running on 512, and you also see it's completely linear. This may be an interesting thing. At the time that we had the project on Jules, there was this heterogeneous cluster, the booster, I don't remember the name, Jules, I think it was cluster, Jules cluster, and there was some CPU only partition. And our code is able to run very efficiently on heterogeneous systems as well. You see here, this is only Jules Booster, and here when you add the other two clusters, you get a speed up, you get still very linear scaling and a small speed up compared to Jules Booster alone. That's on Jules Booster. Then Frontier arrived, and we added a third molecule to the benchmark. This is a different molecule, but now the system gets bigger and bigger. And we still see quite a large, almost ideal scaling. This deviation here is basically because the run is so fast that the setup phase becomes significant. But if we do larger systems, then the run gets longer and probably we will have less deviation for this large number of nodes. GPU acceleration, that was done on this small system, and you also see that we have speed up which is comparable to what we had on Summit or even a little bit better. The last scaling plot that I want to show you is the one on Leonardo and Cineca. This is very, very preliminary because we just started the project, but you also see that we have nice linear scaling in this case. And that's all I wanted to explain. I just want to show the current chrono team. Jack is on the chrono team. He did all the parallelization GPU offloading. This is my team in Tarragona, in Spain. We have Ria still on board, the original developer of the GNOME algorithm. And we have a Paul in Barcelona, and doing mostly applications. And I thank you for your attention.
Any question in the room? Yeah.
Yeah, thank you very much for the interesting talk. I was wondering, why do you have OpenACC and OpenMP target offloading? Is there some benefit for one or the other, and why should users choose the one or the other?
I think that OpenACC is not implemented on the AMD GPUs. It's not available.
Right.
So for Frontier...
So OpenMP target would be for both, right? Available.
Yeah, I guess so. Yes. Yeah, but OpenACC is very much is very efficient on the NVIDIA GPUs.
So OpenACC is better for NVIDIA and OpenMP target is available.
I think so. I think we have to make more detailed benchmarks for that, but that is ongoing work at the moment.
Okay, thanks.
Yeah.
So we also have experience with both OpenACC and OpenMP, and the fact is that some of the constructs that are available in OpenACC that make data transfer control movement of data a little bit, it gives you a better control. And so when you're using NVIDIA GPUs, OpenACC is definitely a better option. It just isn't available with...
What's missing?
What's missing is finer control and data movement. Yes. Yes. Okay, let's talk.
Almost finished.
Looks like every time I make a comment, I run into...
I want to know, so I can fix it. I apologize if that bothers you.
So just a comment that the Cray compiler does support OpenACC and Fortran, right? And on the HPE platform, so including AMD.
Any other comment or discussion? Okay, just that leads me to the maybe general comment or question. It means that on your side, when you're doing benchmarking, your hotspot is somehow impressive scaling. Your hotspot is portability. You understand?
Yeah, because well, the biggest problem that we had was going from the NVIDIA GPUs into the AMD GPUs. That took us quite a while because we implemented OpenMP, that's one thing, and we want to be as general as possible. Yeah.
Okay, and when you do work on this portability, do you have in mind, okay, let's make you have several options actually, indeed, so the discussion, so it's either you are using several libraries.
Yeah, you activate them by when you compile, by the compilation directives.
So somehow your hotspot is portability, but also performance. Like you don't accept to have a, let's say, large decrease from this architecture to another.
No, yeah.
Okay, thank you. Any other questions or comments? Okay, so it's time to get food. Thanks again, Colin.